Fermi paradox. The stars are ancient. The universe is unimaginably vast. There are more galaxies than grains of sand on all the beaches of Earth. Each of those galaxies contains billions of stars, and around those stars orbit untold trillions of planets. Many of them lie within the so-called habitable zone, where conditions might support liquid water, the ingredient we associate most closely with life. Given these numbers, it seems almost statistically impossible that Earth is the only planet with intelligent life. And yet, in all our explorations, observations, and careful listening to the sky, we have found nothing. No alien radio signals, no evidence of spacecraft, no grand interstellar civilizations, just silence. This chilling contradiction between high probability and absence of contact is known as the Fermi paradox, and it has haunted scientists, philosophers, and dreamers for decades. The paradox originated with a simple question asked by physicist Enrico Fermi in 1950. Where is everybody? At the time, the idea of space travel and alien life was a source of both public wonder and scientific curiosity. Fermi's point was razor sharp. If the universe is old and full of potentially habitable worlds, and if life emerges even occasionally, then why hasn't someone, somewhere, made themselves known to us? Why hasn't Earth already been visited or colonized or at least detected? The numbers suggest we should not be alone. But the evidence, or lack thereof, paints a very different picture. To understand why this question is so perplexing, we need only consider the age and scale of our galaxy, the Milky Way. It is over 13 billion years old. That's more than enough time for an intelligent civilization to evolve, build spacefaring technology, and spread across the galaxy, even if they did it slowly. In fact, conservative estimates suggest a technologically advanced civilization could colonize the entire Milky Way in just a few million years. That's a blink of an eye in cosmic terms. So, where are they? One possible answer is that intelligent life is extraordinarily rare. While the building blocks of life, amino acids, carbon chains, and even organic molecules appear throughout space, the leap from chemistry to biology might be far more difficult than we assume. And going from simple microbial life to conscious tool-using intelligence could be even rarer still. Earth may not be one in a million. It may be one in a galaxy, or one in the entire observable universe. In that scenario, we are the miracle, the exception, the voice in the void. But what if intelligent life isn't rare? What if it's common, but also fragile? Some scientists suggest that the Great Filter, the obstacle that prevents civilizations from advancing, isn't behind us, but ahead. Perhaps civilizations routinely emerge, flourish, and then destroy themselves before achieving interstellar travel. Nuclear war, climate collapse, pandemics, or artificial intelligence gone rogue, there are countless existential risks that could wipe out intelligent life shortly after it becomes technologically capable. If this is true, then the silence of the stars may not be a mystery. It may be a warning. There are also theories that posit alien civilizations are indeed out there, but they are deliberately avoiding contact. This idea, known as the zoo hypothesis, suggests that Earth is being observed but left undisturbed, like an experiment or a wildlife preserve. In this view, we're the cosmic animals behind glass. Unaware that we are being watched, perhaps advanced beings have agreed to avoid interfering with primitive species like ours. After all, we might not be ready. We can't even cooperate with one another on a planetary level. What would we do if faced with something truly alien? Another possibility is that we are simply looking in the wrong way at the wrong time. Our radio telescopes have only been scanning the skies for about 100 years. That's a tiny window, even in the life of a single star. What if alien civilizations use different forms of communication, gravitational waves, quantum entanglement, or something we haven't even discovered yet? Or what if their signals passed us long ago, before humans had even emerged? We may be like people staring into the ocean, hoping to hear whale song through a glass bottle. Some theorists even propose that advanced civilizations have moved on from physical existence altogether. They might have uploaded their minds into machines, or retreated into artificial realities, no longer needing to explore the stars. If they live in simulated universes of their own design, they may have no interest in contacting biological life. In that case, the silence isn't neglect. They've already found what they were searching for, and we are simply irrelevant to their purpose. The Fermi paradox also opens the door to more unsettling possibilities. Perhaps there is something in the universe that destroys civilizations once they become visible. A predator, a force, a natural phenomenon that wipes out any race that dares to broadcast its presence. If this is true, then the silence is not a mystery, it's an act of survival. Civilizations may go dark to avoid detection, hiding in fear from whatever lurks between the stars. And then there are the theories that suggest we are simply not listening with the right mindset. We tend to imagine aliens as being like us, carbon-based, hierarchical, driven by conquest or curiosity. But what if they are fundamentally different? What if they don't build cities, launch rockets, or send signals? What if their form of intelligence is spread across a planet, or exists in patterns we cannot yet detect? The silence may not be real at all. It may just be the result of our limited imagination. The Fermi paradox doesn't just question the existence of aliens, it questions us, our assumptions, our expectations, our place in the cosmos. Are we truly alone, or are we simply not yet ready to see what lies beyond our little blue planet? The paradox forces us to hold two opposing ideas in our minds at once, that intelligent life should be common, and yet there is no sign of it. This tension reveals more about the mystery of existence than any single answer could. Maybe one day we will find a signal, or a spacecraft, or ruins on a distant world. Maybe one day the silence will end, but until then, the Fermi paradox remains one of the greatest cosmic riddles, a mirror in which we see both our loneliness and our potential. In its silence, the universe invites us to listen more closely, to think more deeply, and to wonder endlessly. Polchinski's paradox. Imagine a universe where time isn't a straight line, but a loop, a place where past and future can meet, where cause and effect fold into themselves like a snake eating its own tail. In 1991, physicist Joseph Polchinski proposed a mind-bending scenario that would take the notion of time travel and hurl it into a realm of paradox that still puzzles physicists today. His thought experiment, often called the Polchinski paradox or the billiard ball wormhole paradox, asks a deceptively simple question: what happens when an object travels back in time and interferes with its own past? At first, it might sound like a clever sci-fi riddle, but buried within it are deep implications about the nature of time, reality, and the strange rules that govern our universe. To grasp this paradox, you need only picture a billiard ball, ordinary, solid, and harmless. Now imagine that this billiard ball is rolling toward a peculiar kind of portal, one that doesn't take you to another place, but to another time. Specifically, it's a wormhole. A theoretical tunnel through space-time. If this wormhole exists, then entering one mouth of it could allow the ball to emerge in the past seconds before it began its journey. The ball could, in theory, collide with its past self. It might nudge itself slightly off course, changing the very trajectory that would have sent it through the wormhole in the first place. Herein lies the paradox. If the ball collides with its past self in such a way that it prevents itself from ever entering the wormhole, then the collision never happens. But if the collision never happens, the ball rolls uninterrupted into the wormhole and emerges in the past, only to collide with itself again. It's a feedback loop of contradiction, a logical dead end. The past is changed by an event that can only occur if the past remains unchanged. This isn't just a trick of language or logic. It's a real physical dilemma, one that threatens to unravel the consistency of cause and effect. What Polchinski demonstrated was that even in a universe governed by deterministic physics, where the laws of motion and energy are well understood, A time-traveling billiard ball could create a situation where no consistent outcome exists. And that is deeply troubling, because the foundation of physics is consistent. The laws of nature aren't supposed to produce paradoxes, they're supposed to explain the world. What makes the Polchinski paradox so fascinating is that it uses simple objects, no complicated machines or sci-fi speculation, just a ball, a wormhole, and time. Yet the implications are profound. It suggests that if wormholes allow time travel, and if objects can interact with their own past, then reality must find a way to resolve the paradox. One proposed resolution is the idea of self-consistency. This principle, championed by physicist Igor Novikov, suggests that any action taken by a time traveler must be consistent with the timeline they emerged from. In other words, the universe wouldn't allow contradictions. Applied to the billiard ball, this means that the ball would indeed travel back in time, but it would only nudge its past self in just the right way that it still ends up entering the wormhole. The collision would be gentle, a soft tap that changes nothing important. No paradox arises because everything that happens was always part of the timeline. But this solution raises deeper questions. Is the universe constrained by consistency? Do all timelines have to be self-correcting? And if so, does that mean free will disappears the moment time travel becomes possible? If every action must be consistent with history, then time travelers cannot change anything, only fulfill what's already destined. That's a haunting thought. It suggests a universe where everything is scripted, even the choices that feel spontaneous. The billiard ball can't choose to strike harder or softer. It must do exactly what it always did, and so must we. Still, some physicists aren't satisfied with this neat resolution. They argue that consistency might not be enough to save us from paradox. What if the ball strikes itself in such a way that multiple outcomes are equally plausible? What if quantum uncertainty enters the picture, making the ball's position slightly indeterminate? In that case, reality might split. One universe for each possible outcome, a multiverse born from every flick of the cue. This leads to another proposed resolution, the many worlds interpretation. According to this idea, the billiard ball doesn't face a contradiction because each possibility plays out in a separate timeline. In one universe, the ball hits itself and avoids the wormhole. In another, it misses and enters the wormhole. Both outcomes happen, just in parallel realities. No paradox, just branching possibilities. But if reality works this way, then time travel doesn't take you into your own past, it takes you into a copy of it. You can interact with your past self, even destroy it, without affecting your original timeline. The past isn't fixed because it's no longer your past, it's someone else's. This may resolve the paradox, but it does so by abandoning the idea of a single, coherent universe. Yet some find this even more unsettling. If every choice spawns a new universe, then existence becomes an infinite web of branching timelines, each filled with versions of us making every possible decision. The billiard ball becomes a symbol of this chaos, a tiny object whose motion fractures reality into an uncountable number of worlds. What makes Polchinski's paradox so powerful is its elegance. It distills the problem of time travel into a form that can be analyzed, measured, and debated. There's no need for time machines or human involvement, just a single looping path and an object simple enough to obey known laws. And in that simplicity lies its danger, because if even a billiard ball can collapse logic, what hope is there for more complex beings like us? The paradox forces us to confront a truth about time that remains unresolved. We don't fully understand it. We experience it as a flow, but physics treats it as a dimension. We remember the past, but cannot see the future, even though both may already exist in the fabric of space-time. Time travel, whether real or not, exposes the fractures in our understanding of reality. It reveals that our universe might be stranger than we ever imagined, and that the smallest actions, like a billiard ball striking itself, can open doorways to impossibility. Polchinski's paradox hasn't been solved, because it isn't meant to be. Like all great paradoxes, it's a mirror we hold up to our assumptions. It asks not only what is possible, but what is consistent. It reminds us that, even in a universe governed by law and order, time can twist those laws into knots we can't yet untangle. And perhaps, buried in those knots, is a truth we're not ready to see. Red Sky Paradox. The universe stretches endlessly around us, a vast sea of stars scattered like fireflies across a velvet sky. Yet, among this breathtaking cosmic expanse, one kind of star dominates the numbers more than any other: the humble red dwarf. Small, cool, and faint compared to our sun, red dwarfs make up nearly 75% of the stars in the Milky Way. They are the silent majority, burning steadily for trillions of years, offering long-lasting stability that should, in theory, provide perfect conditions for life to thrive. Their planets, orbiting close to these dim suns, could bask in gentle warmth for eons. Statistically speaking, if life were common in the cosmos, we would expect to find it flourishing around red dwarfs. Yet we have not. This puzzling absence is known as the red sky paradox, and it challenges some of our deepest assumptions about where life might emerge in the universe. When scientists first began scanning the skies for habitable worlds, red dwarfs quickly caught their attention. Their sheer numbers meant there would be countless planets orbiting within the so-called habitable zone, the sweet spot where liquid water could exist. And because red dwarfs are so dim, their habitable zones are close in, making the planets easier to detect using modern methods like the transit technique, where a planet dims its star's light as it passes in front of it. Missions like Kepler and TESS revealed that small, rocky planets are common around red dwarfs. Some, like Proxima Centauri b, lie tantalizingly close, only 4 light-years away. Everything seemed perfectly aligned for a universe brimming with life under crimson skies. And yet, as we listened for radio signals, searched for chemical signs in alien atmospheres, and modeled the possibilities of alien ecosystems, we found nothing. No hints of life, no biosignatures, no whispers from distant civilizations, just silence. The red sky paradox emerges from this contradiction. The stars that should most abundantly host life appear barren. If red dwarfs are so numerous and long-lived, why is the cosmos not teeming with life orbiting these faint red suns? One possible answer lies in the nature of red dwarfs themselves. Unlike our relatively stable sun, young red dwarfs are fiercely temperamental. In their youth, they unleash powerful flares, blasts of radiation, and charged particles capable of stripping away a planet's atmosphere. For planets huddled close to their parent stars, this could be devastating. Even a single massive flare could blast away the protective layer that shields life from harmful ultraviolet and X-ray radiation. Without an atmosphere, liquid water would evaporate, organic molecules would break apart, and any fragile beginnings of life would be snuffed out before they had a chance to flourish. Even if a planet manages to retain some of its atmosphere, it might still be locked into a phenomenon called tidal locking. Because the habitable zone around a red dwarf is so close, gravitational forces could cause one side of the planet to perpetually face the star, while the other side remains in eternal darkness. One hemisphere would bake under constant daylight, while the other would freeze in endless night. This creates extreme temperature differences that could make it difficult for life as we know it to gain a foothold. Harsh winds, turbulent storms, and unstable climates might dominate these tidally locked worlds, reducing the chances for stable, life-friendly environments. There's also the issue of stellar longevity. While red dwarfs live far longer than sun-like stars, trillions of years compared to billions, their early violent phase could delay the emergence of life for billions of years. Life on Earth appeared relatively quickly after the planet cooled, but if red dwarf planets must endure hundreds of millions or even billions of years of intense radiation before calming down, the process of abiogenesis, life arising from non-living matter, might be delayed or prevented altogether. By the time conditions stabilize, it could already be too late, or the building blocks of life could have been irreparably damaged. Another subtle but profound problem lies in the energy spectrum of red dwarfs. These stars emit most of their light in the infrared, not the visible spectrum we are used to. Photosynthesis as we know it relies heavily on visible light, particularly blue and red wavelengths. Could alien plants, if they exist, evolve to capture energy from infrared light? It's possible, but infrared photons carry less energy than visible light photons, meaning that any biological processes dependent on light would have to operate differently, perhaps less efficiently. The very foundation of energy use for life might be fundamentally limited around these stars. Even if life does manage to emerge, it faces another hurdle: detectability. Because red dwarf planets orbit so close to their stars, they are often shrouded in their star's glare. The chemical signatures of life, oxygen, methane, water vapor, might exist in their atmospheres, but be drowned out by the overwhelming infrared radiation. Our instruments might not be sensitive enough or tuned correctly to pick up these subtle hints. In this view, the red sky paradox isn't evidence of absence, it's evidence of our technological blindness. There's also the chilling possibility that life around red dwarfs is common but primitive. Microbial life might thrive in subsurface oceans, in protected caves, or deep within crusts where radiation cannot penetrate. These ecosystems, hidden from view, would leave no obvious traces in the atmosphere for our telescopes to detect. Complex, multicellular life might be rare or non-existent, leaving vast stretches of cosmic time populated only by invisible microbes. From our distant perspective, these worlds would seem dead, even though they teemed with life just below the surface. Some scientists even speculate that we might be biased by our own planetary history. Earth's path to life was shaped by unique factors: our moon stabilizing our tilt, plate tectonics recycling nutrients, and a magnetic field protecting us from solar winds. Perhaps these conditions are rare, even among red dwarf planets. Maybe most worlds orbiting red dwarfs are missing one or more crucial ingredients, and thus remain barren deserts or toxic wastelands, incapable of nurturing life beyond simple chemistry. Another angle is cultural. Perhaps intelligent civilizations, if they arise around red dwarfs, simply have different priorities. With stars that live trillions of years, there would be little urgency to expand, explore, or broadcast signals. A civilization under a red sky might think in terms of millions of years instead of centuries. Their pace of development could be so slow that in our brief moment of cosmic awareness, we miss them entirely. Or they might choose to live inwardly, perfecting virtual realities, hiding their existence, or simply not caring to announce themselves to the stars. The red sky paradox ultimately invites us to rethink our assumptions about life in the universe. We often imagine Earth-like planets orbiting sun-like stars, with familiar conditions and recognizable biosignatures. But nature rarely caters to human expectations. If life exists around red dwarfs, it may look nothing like life on Earth. It may emerge differently, evolve differently, and communicate or not communicate in ways we can barely begin to imagine. And so we are left with a cosmic mystery. The skies are filled with countless red suns, each with its own hidden worlds, each with the potential to host life, and yet, from where we stand, they are silent, dark, and empty. Perhaps the universe is still hiding its secrets. Or perhaps, against all odds, Earth really is an oasis in a desert of dead worlds. The red sky paradox forces us to confront this possibility with humility, patience, and wonder. Maybe one day, with better instruments and deeper understanding, we will crack the silence. Maybe a faint chemical fingerprint in a distant atmosphere will whisper of alien life thriving under a red sky. Or maybe the answer will elude us forever, a reminder that in the grand tapestry of the cosmos, some threads remain hidden, woven just beyond the reach of human hands and human hope. Bootstrap paradox. Time, as we normally understand it, is a river flowing in one direction, from the past to the future, always moving forward. Cause precedes effect, action leads to consequence, and creation follows from origin. This order feels natural, even necessary. But what if time didn't work that way? What if an object or a piece of information could exist without ever being created, looping endlessly through time with no true beginning? This is the heart of the bootstrap paradox, a time travel riddle that breaks the very foundations of causality and leaves us questioning whether reality itself can hold steady under such strange loops. Imagine a time traveler who decides to visit the past. Before leaving, he packs a copy of Shakespeare's Hamlet into his bag. Upon arriving centuries earlier, he hands the book to a young Shakespeare, who copies it down and claims it as his own masterpiece. The book is printed, performed, and celebrated throughout history. Centuries later, the time traveler grows up, reads Hamlet, and decides to bring a copy back in time, thus closing the loop. But now the question arises, who wrote Hamlet? Shakespeare received it from the time traveler, who received it from Shakespeare. There is no true origin. The play exists in an endless cycle, uncreated, yet very real. This is the bootstrap paradox in its purest form. Named after the old expression, pulling oneself up by one's bootstraps, an impossible act of self-creation, it describes situations where an object, person, or information is trapped in a self-contained causal loop. It exists because it exists. It is its own cause and effect, with no outside origin to explain how it came into being. Time travel literature and science fiction are filled with examples of this paradox, but its implications stretch far beyond storytelling. It challenges our deepest intuitions about time, causality, and the very nature of existence. To better understand the paradox, consider a simpler version involving an object. Suppose a scientist in the future builds a time machine. One day, an older version of herself appears, hands her the blueprints for the machine, and disappears. The young scientist studies the blueprints, builds the time machine, and grows older. When the time comes, she travels back to deliver the blueprints to her younger self. But where did the design originally come from? It was never invented, it was simply passed from future to past, existing in a closed loop with no external source. At first glance, this seems impossible. Surely everything must have an origin, a first cause, a beginning. But the bootstrap paradox suggests otherwise. In the realm of time travel, causality can bend back on itself, creating objects and information that exist independently of any traditional origin. They are self-sustaining. They are causally bootstrapped into existence. Physicists who explore the theoretical possibilities of time travel, especially within the framework of general relativity, take the bootstrap paradox seriously. Solutions to Einstein's equations suggest that closed time-like curves might exist, allowing for paths through space-time that loop back on themselves. If such curves are possible, then the bootstrap paradox is not just a philosophical puzzle. It could be a real feature of the universe. But how could reality accommodate such strange loops without collapsing into incoherence? One proposal is the Novikov self-consistency principle, which states that any event that would cause a paradox is forbidden. Under this principle, events on a closed time-like curve must be self-consistent, meaning that the timeline cannot be altered in ways that would create contradictions. In the case of the bootstrap paradox, the existence of the book, the blueprints, or the object is simply a self-consistent feature of the timeline. There is no contradiction because the loop is closed and stable. The object exists because it always did, and that's the end of the story. But for many, this feels unsatisfying. It seems to undermine the very idea of causality as we know it. If objects or information can exist without being created, then our understanding of the universe's fundamental laws may be incomplete. Creation ex nihilo, from nothing, has always been the domain of the miraculous, not the physical. The bootstrap paradox blurs the line between physics and metaphysics, suggesting that under certain conditions existence can be self-generated. Some physicists and philosophers argue that while the bootstrap paradox is logically coherent within certain models of time travel, it may be practically impossible. Quantum effects, information entropy, and the second law of thermodynamics could conspire to prevent perfect causal loops. Over time, imperfections would accumulate, causing the loop to unravel. In this view, the paradox is an intriguing thought experiment, but unlikely to manifest in reality. Others, however, embrace the paradox as a window into a deeper understanding of time. Perhaps our linear conception of time is simply an illusion, a useful approximation that breaks down under extreme conditions. If the universe itself has no beginning and no end, if it is a closed, self-contained entity, then causal loops might be not just possible, but natural. Existence itself could be a vast cosmic bootstrap, a reality without origin, spinning eternally in the dark. The bootstrap paradox also invites profound questions about identity and authorship. If a person receives information from the future and acts upon it, are they the true author of their actions? If Shakespeare's plays came from a time traveler rather than Shakespeare's own mind, what does that mean for creativity, ownership, and history? In a world shaped by bootstrap loops, the boundaries between creator and creation dissolve, leaving only the loop itself as the ultimate reality. Science fiction has long been fascinated by the bootstrap paradox. Movies like Predestination, 12 Monkeys, and episodes of Doctor Who explore its mind-bending implications. In each story, characters struggle with the realization that their actions are part of a self-fulfilling cycle. They are trapped by destiny, yet paradoxically free to act but only in ways that sustain the loop. The tension between freedom and determinism lies at the heart of every bootstrap narrative. And perhaps that is why the bootstrap paradox resonates so deeply. It mirrors our own existential questions about meaning, purpose, and the origin of life. Where did the universe come from? What caused the first spark of being? If time travel were possible, would we find ourselves trapped in loops of our own making, endlessly reciting the same cosmic story without a first page? The bootstrap paradox may not offer answers. Instead, it holds up a mirror to our assumptions, forcing us to confront the possibility that cause and effect, beginning and end, might be far stranger and far more intertwined than we dare to imagine. It suggests a universe where some things simply are, not because they were created, but because they are woven into the fabric of existence itself. As we continue to explore the mysteries of time, space, and reality, the bootstrap paradox stands as a timeless reminder. Not all riddles are meant to be solved. Some are meant to expand our minds, to stretch our imaginations beyond the comfort of logic, and to invite us to peer into the loops and echoes that may lie at the heart of all things. Grandfather paradox. Time travel has long captured the human imagination, offering a tantalizing escape from the rigid march of minutes and hours. The thought of stepping backward into history, of changing events long set in stone, opens endless possibilities and endless dangers. Among the most famous and haunting dilemmas that arise from this fantasy is the grandfather paradox, a problem so profound that it shakes the very foundations of causality itself. At its heart, the paradox asks a simple but devastating question. What happens if you travel back in time and prevent your own existence? What if you killed your grandfather before your parent was born? If you succeed, you could never have been born to travel back and do it. But if you were never born, who killed your grandfather? The circle tightens, logic collapses, and we are left staring into the abyss of contradiction. The classic version of the paradox is brutal in its simplicity. You invent a time machine. You travel to the past, decades before your birth. You seek out your young grandfather, perhaps before he meets your grandmother. For whatever reason, malice, accident, or curiosity, you cause his death. With your grandfather gone, your father or mother is never born, and so you are never born. Yet without your existence, you could not have traveled back to kill him. Without the act, he survives. And so you are born after all, only to go back and kill him again. The paradox spins in an endless, impossible loop, where cause and effect eat each other alive. This contradiction strikes at the most basic structure of reality, the chain of events where causes produce effects. In our normal experience, the past is fixed and immutable. What has happened cannot be undone. The grandfather paradox, by introducing time travel into this chain, tears it apart. It suggests a scenario where an event can simultaneously occur and not occur depending on its own consequences. In effect, it creates a logical impossibility, an event that prevents the conditions necessary for its own existence. Philosophers, physicists, and storytellers have grappled with the grandfather paradox for decades. Some propose that it proves time travel to the past is impossible, at least in any form where changes can be made. In this view, the universe guards its own consistency with unbreakable laws. No matter how clever your time machine, you cannot alter events that have already happened. If you go back in time, you will find that circumstances conspire to prevent you from killing your grandfather. The gun jams. You have a change of heart. Fate intervenes. Reality bends, subtly or forcefully, to preserve the timeline. This idea is often referred to as the self-consistency principle. It was most famously advanced by physicist Igor Novikov, who argued that time travel must be consistent with history. In a self-consistent universe, any attempt to change the past is doomed to fail, not because of some supernatural force, but because of the inherent structure of space-time itself. You might be able to visit the past, observe it, even participate in events, but you cannot create contradiction. You are bound by history as surely as a leaf is bound by the current of a river. But what if reality isn't so accommodating? Some theorists suggest that attempts to change the past could create branching timelines or parallel universes. In this many worlds interpretation, when you travel back and kill your grandfather, you do not erase yourself in your original timeline. Instead, you create a new timeline where your grandfather is dead and you were never born, but the version of you who made the trip came from a different timeline, one where your grandfather survived. In this way, causality remains intact within each universe, but the broader multiverse splits into countless divergent realities. This solution saves logic, but at the cost of simplicity. It multiplies worlds without end, creating a labyrinth of branching possibilities for every action. Kill your grandfather and you spawn a new universe. Save him and you remain in the one you left. The grandfather paradox dissolves not through prevention, but through multiplication. Reality becomes not a single thread, but an endless tapestry, with each choice weaving its own path. Still, the grandfather paradox remains unsettling. Even if branching timelines are possible, the original problem highlights a profound instability at the heart of time travel. It shows that our intuitive understanding of time as a steady, unbreakable chain of cause and effect cannot easily accommodate journeys into the past. If time can be rewritten, then history becomes a shifting sea, and identity itself grows uncertain. If you can erase your own existence, what does it mean to be you? How stable is memory, lineage, or fate? Beyond its physical implications, the grandfather paradox also touches deep psychological fears. It embodies the terror of unintended consequences, the anxiety that our actions could ripple backward and undo everything we are. It speaks to the fragility of existence, the precarious chain of accidents and choices that brought each of us into being. One broken link and we vanish. It forces us to confront how thin and miraculous the thread of life truly is. Stories that explore the grandfather paradox often use it as a metaphor for guilt, regret, and the longing to undo the past. In tales of time travelers trying to save loved ones or prevent tragedies, the paradox lurks in the background, whispering that some things cannot be changed without breaking everything. It reminds us that the past shapes us, even when it wounds us, and that tampering with it might cost more than we can bear. Yet there is also a strange beauty to the grandfather paradox. It reveals the interconnectedness of time and identity. It shows that we are not isolated points, but links in a vast chain stretching backward through generations. Our existence depends not just on our choices, but on countless choices made long before we were born. Each life is a story written by the hands of ancestors we may never know, and changing even one word of that story could erase the entire book. Some speculative solutions to the paradox go even deeper, suggesting that free will itself might be an illusion. If the past cannot be changed, then our actions are predetermined, woven into the fabric of space-time. In such a universe, time travelers are not agents of change, but actors following a script already written. We might feel free, but every decision, every breath, is already part of a self-consistent history that cannot be altered. The grandfather paradox thus challenges not only our ideas about time, but about freedom, choice, and the nature of reality itself. The grandfather paradox stands as a towering question mark over the dream of time travel. It warns that stepping into the past is not a casual adventure, but a profound and perilous act, fraught with consequences we may not understand. It reminds us that time, for all its mysteries, has a structure, a logic, that may resist our attempts to tamper with it. Whether through self-consistency, branching universes, or some deeper principle yet undiscovered, the paradox hints that time protects itself, fiercely and implacably. Perhaps that is why, despite our fascination with time machines and journeys into history, we remain bound to the present. Perhaps time, in its quiet wisdom, knows that some doors must remain closed, not out of cruelty, but out of mercy. For in those closed loops, those impossible contradictions, lies the dark heart of time travel's most haunting lesson. That the past, once lived, belongs to itself, and to change it is to risk unraveling everything, including ourselves. Methuselah Star Paradox. In the cold reaches of our galaxy, amid the ancient stellar populations drifting through the halo of the Milky Way, there exists a star so old that it seems to contradict the very fabric of time itself. Astronomers have named it HD 14283, but it's better known by its biblical nickname, the Methuselah Star. It earned this name not for mythological flair, but because of a profound and disquieting mystery. When astronomers first measured its age, the results sent a ripple through the scientific community. The star appeared to be older than the universe, and not just by a trivial margin, by hundreds of millions of years. This strange and unsettling result created what we now call the Methuselah Star Paradox, a scientific puzzle that calls into question our deepest understanding of cosmic time, the formation of stars, and the birth of the universe itself. To appreciate the strangeness of the Methuselah Star, we must first understand how we measure the age of the cosmos. The Big Bang Theory, which describes the origin of the universe as a rapid expansion from an incredibly hot, dense state, provides a timeline that's been refined by generations of observation. Through the study of cosmic microwave background radiation, the afterglow of the Big Bang, and the rate at which galaxies are receding from one another, scientists have converged on a remarkably precise figure. The universe is approximately 13.8 billion years old. This number acts as a cosmic ceiling. Nothing in the universe, logically, should be older than that. Nothing could exist before existence itself. And yet, HD 1433 told a different story. Nestled just 190 light-years from Earth, this metal-poor subgiant star seemed unremarkable at first glance. But when scientists analyzed its light, specifically the chemical composition encoded in its spectrum, they discovered something unusual. The star had incredibly low levels of heavier elements like iron, carbon, and oxygen. This indicated that it formed very early in the universe's history, before these elements were forged in the nuclear furnaces of other stars and scattered by supernovae. In essence, it was a second-generation star, born from primordial hydrogen and helium, with only the faintest trace of contamination. Using models of stellar evolution, scientists determined how fast the Methuselah star had burned through its fuel. By estimating its mass, luminosity, and composition, they calculated an age of around 14.5 billion years. That figure, stubborn and consistent, suggested that the star was older than the universe itself by at least 700 million years. The implications were staggering. If the star's age was accurate, it meant either the universe was older than we thought, or our models of stellar aging were flawed, or perhaps, most unsettling of all, there was something fundamentally wrong with our understanding of time and space. This paradox forced astronomers into deep reflection. How could a star predate the very conditions that allowed stars to form? One possibility was that the age estimate was simply wrong, perhaps due to uncertainties in stellar modeling. After all, determining the age of a star isn't like reading a calendar. It's an intricate dance of assumptions, measurements, and simulations. Small changes in metallicity or distance can ripple through the calculations and shift the final result. And in the case of HD 1440283, that margin of error, though small, was enough to bring its estimated age down to just below the age of the universe, hovering around 13.7 billion years when revised. But even this adjusted estimate places the Methuselah star at the very edge of cosmic time. If the universe began 13.8 billion years ago and the star formed shortly after, it must have done so almost immediately, within a few 100 million years of the Big Bang. That's shockingly early. At that time, the universe was still opaque with primordial gas. The first stars, called Population 3 stars, were just beginning to ignite. These first stars were massive and short-lived, living fast and dying young, enriching the cosmos with the heavier elements necessary for new generations of stars. HD 1.3 must have formed from the debris of those first explosions, placing it as one of the oldest known relics of the cosmos. The Methuselah star, then, becomes not just a puzzle, but a time capsule. It contains within its light the story of an era we can barely imagine, a universe still cooling, still clearing, still learning how to form galaxies and planets. Its paradoxical age, rather than being a contradiction, may instead point to the limits of our precision and understanding. The closer we get to the beginning of time, the more sensitive our instruments must be, and the more we must refine our models. Even a slight revision in the expansion rate of the universe, the Hubble constant, can shift the cosmic timeline and resolve the apparent discrepancy. There is also the philosophical weight of the Methuselah star. Its paradox is not just numerical, it's existential. It invites us to question the boundaries of knowledge. How do we truly measure the age of something that has outlived civilizations, galaxies, and epochs? When our tools approach the origin of all things, how confident can we be in our reconstructions? The Methuselah star stands as a silent guardian of deep time, a stellar archaeologist's dream that reminds us of how little we still know. Some have speculated more wildly, wondering if stars like HD 1440283 could be evidence of pre-Big Bang structures, relics of a cosmos that existed before our own. While mainstream science treats such ideas with caution, they reflect a growing awareness that the universe may have more layers, more cycles, more mysteries than we dare to imagine. What if the Big Bang wasn't the beginning, but just the latest chapter? What if time itself loops or branches, leaving remnants behind like forgotten pages from older drafts of the universe? The Methuselah star paradox serves not to debunk the Big Bang, but to sharpen our focus. It forces us to ask better questions, refine our techniques, and remain humble before the vast canvas of the cosmos. As our instruments improve and our theories evolve, the paradox may dissolve into clarity or deepen into new mystery. Either way, the star continues to shine, patiently orbiting in our galactic halo, whispering secrets of a time when there were no humans, no Earth, and perhaps not even galaxies as we know them. Its light, traveling for nearly 200 years before touching our telescopes, carries with it the echoes of a universe still awakening. And in that light, we glimpse the paradox not as a flaw in our science, but as a feature of our curiosity, a reminder that even the oldest stars can surprise us, and that the universe, for all its age, is still young in the face of wonder. Schrödinger's cat. In the world of everyday experience, reality feels concrete. A chair is a chair, whether we look at it or not. A light is either on or off. A cat is either alive or dead. But in the realm of quantum mechanics, this certainty dissolves into probabilities, and the very act of observing seems to shape what is real. Nowhere is this bizarre notion more vividly captured than in the thought experiment known as Schrödinger's cat, a strange and haunting metaphor that forces us to confront a world where reality may not exist until we observe it. It is not a riddle about cats, really, but a question about the nature of existence itself, told through a sealed box, a quantum particle, and the fate of an unseen feline. The paradox was first proposed in 1935 by Austrian physicist Erwin Schrödinger, not as a literal scientific proposal, but as a critique of the Copenhagen interpretation of quantum mechanics, the dominant theory of the time. In this interpretation, a quantum particle, such as an electron or atom, doesn't exist in one state or another until it is measured. Until observed, it occupies a superposition, a blend of all possible states simultaneously. Once measured, the superposition collapses into a single, definite state. Schrödinger found this deeply unsettling. He wanted to expose the absurdity of this idea by applying it to the macroscopic world we know and trust. So he imagined this scenario. A cat is placed inside a sealed box. Inside the box is a tiny amount of a radioactive substance, so small that there is a 50% chance that one atom will decay in the next hour and a 50% chance that it will not. Also in the box is a Geiger counter to detect the decay, a vial of poison, and a hammer rigged to break the vial if the Geiger counter registers radiation. If the atom decays, the hammer breaks the vial and the poison is released, killing the cat. If the atom does not decay, the cat lives. The entire system is sealed and cannot be observed from the outside. Now comes the twist. According to quantum mechanics, until the atom is observed, it exists in a superposition of decayed and not decayed. Therefore, the Geiger counter has both triggered and not triggered. The vial is both broken and intact, and most disturbingly, the cat is both dead and alive, simultaneously. Only when the box is opened and the system is observed does the wave function collapse, resolving into one outcome or the other. The cat until then is in a paradoxical limbo, not merely unknown, but actually in both states at once. This mental experiment, though fictional, exposes the core tension at the heart of quantum physics. It confronts us with a deeply counterintuitive idea that reality, at its most fundamental level, might not be fixed until we look at it. In the quantum world, the rules of logic we rely on begin to blur. A particle can be in multiple places at once, spin in opposite directions, and interfere with itself as though it travels all paths at the same time. But what happens when those strange rules are scaled up to the world we see and touch? Schrödinger's cat forces that question with uncomfortable clarity. For decades, physicists have debated the meaning of this paradox. Is the cat really both dead and alive, or is it simply our knowledge of the system that is uncertain? Some interpretations argue that superposition is just a mathematical tool to describe our ignorance. Others, like the many worlds interpretation, take the paradox at face value. In that view, when the box is opened, the universe splits into two. In one, the cat is alive. In the other, the cat is dead. Both outcomes are real, but they exist in separate parallel realities. We only experience one of them, but the other continues without us. Then there's the question of what counts as an observer. Is it a conscious mind? A camera? A measuring device? If an electron exists in multiple states until measured, what does it mean to measure it? Does the cat, in some sense, observe itself? These questions reveal the blurry boundary between the quantum and classical worlds, a frontier that remains one of the most mysterious in all of physics. Some experiments have shown that quantum effects can persist even in large molecules, suggesting that superposition may extend farther into the macro world than once believed. Over time, scientists have developed interpretations that seek to resolve or at least reframe the paradox. The decoherence theory, for example, explains how quantum systems interacting with their environment lose their superposition quickly. In the case of Schrödinger's cat, the environment inside the box, air molecules, vibrations, thermal radiation, might cause the quantum superposition to decohere, before we even open the lid. From this perspective, the cat is already dead or alive before observation, because the delicate quantum state could not survive in such a chaotic environment. Decoherence doesn't eliminate the mystery, but it offers a mechanism for how classical reality emerges from quantum possibilities. Still, the philosophical implications of Schrödinger's cat remain profound. If observation plays such a central role in determining outcomes, what does that say about consciousness? Some interpretations, like those loosely inspired by the ideas of physicist Eugene Wigner, suggest that a conscious observer is required to collapse the wave function. This leads to a deeply anthropocentric and controversial view, where mind itself becomes entangled with the structure of reality. Could the universe require consciousness to become real? Or is this merely an artifact of our inability to separate observer from observed? Modern experiments in quantum physics have added nuance to these debates. Delayed choice experiments, quantum erasers, and entanglement tests continue to push the boundaries of what we think we understand. Yet, for all the complexity of these setups, the ghost of the cat remains. It reminds us that behind the technical language and precise mathematics of quantum theory, there lies a fundamental mystery, a universe that behaves differently when we watch it, a reality that may not settle into being until it's called upon to do so. In a way, Schrödinger's cat serves not only as a paradox, but as a parable. It teaches us that our perceptions and assumptions about reality may be deeply limited. We are used to thinking of truth as absolute, of events as happening in one way or another. But quantum mechanics tells us that reality may be richer, stranger, and more layered than we ever imagined. It asks us to embrace ambiguity, to accept that the deepest truths may not conform to the categories we rely on. The cat in the box is not just a curiosity, it is a symbol of our struggle to understand a world that seems to shift under our gaze. And so the box remains closed in our minds, the cat suspended in quantum ambiguity, inviting us to ask what it really means to know something, to observe it, to believe it is real. Whether dead, alive, or both, the cat will continue to haunt the intersection between physics and philosophy, science and mystery, certainty and doubt. It will sit silently in its paradox, as all of reality balances on the edge of a question still unanswered. What is the nature of observation, and what does it make real? Double-slit experiment paradox. In the grand pursuit of understanding the universe, few scientific experiments have ever provoked more wonder, confusion, and philosophical intrigue than the double-slit experiment. It is often described as the most elegant and mysterious demonstration in all of physics. At first glance, it seems simple. A beam of particles is directed at a barrier with two slits, and the resulting pattern is observed on a screen behind. But hidden within this simplicity is a profound and disorienting truth. When we watch particles closely, they change their behavior. They shift from acting like waves to behaving like particles, from probabilities to certainties, from a cloud of possibilities to a defined dot in space. This is the paradox at the heart of quantum mechanics, the idea that the very act of observation alters the reality being observed. To understand the double-slit experiment, we must first begin with light. For centuries, scientists debated whether light was made of particles or waves. Isaac Newton championed the particle theory, while others, like Thomas Young, argued for waves. It was Young who, in the early 1800s, performed the first version of the double-slit experiment. He passed light through two narrow slits and observed the pattern that emerged on a screen. Rather than two distinct lines, which one would expect from particles, he saw a series of light and dark fringes, an interference pattern characteristic of waves. The light seemed to be behaving like ripples in water, with the waves from each slit overlapping, amplifying each other in some places and canceling out in others. This wave behavior of light was accepted for a time until the 20th century, when quantum mechanics emerged. Scientists discovered that light could also behave like a stream of discrete particles called photons. These photons could strike a metal surface and eject electrons, a phenomenon known as the photoelectric effect, which could only be explained if light had particle-like properties. This duality, where light acts both as a wave and a particle depending on how it's measured, became one of the foundational mysteries of quantum physics. But the true strangeness revealed itself when scientists revisited the double-slit experiment using not waves of light but individual particles, like electrons. They fired one electron at a time toward the slitted barrier, expecting that, over time, the electrons would pass through one slit or the other and build up two distinct lines on the screen. But that's not what happened. Even when fired one by one, the electrons formed an interference pattern over time, the same pattern created by waves. Each individual electron somehow behaved like a wave, going through both slits simultaneously and interfering with itself. It was as if each particle was not a point traveling along a path, but a probability cloud spread out across space, experiencing all possible paths at once. Then came the paradox. What would happen if we placed a detector at the slits to see which slit each electron actually passed through? If we observed their path, wouldn't we finally confirm that the electron went through one slit or the other? When scientists did exactly that, the interference pattern vanished. Suddenly, the electrons behaved like ordinary particles again. They chose a path, left slit or right slit, and the resulting image on the screen showed two distinct clusters. The act of observation had collapsed their behavior from wave-like to particle-like. Something about watching the particle forced it to decide on a definite state. The question was no longer about how they traveled, but how the very attempt to observe changed the outcome. This is the essence of the double-slit experiment paradox. Unobserved, particles behave like waves of potential, exploring multiple paths at once, spreading out through space, interfering with themselves. Observed, they snap into one path, one slit, one result. Our act of measurement collapses their superposition into a single outcome. It's as if the universe is suspended in a web of possibility until we demand a concrete answer. Then and only then does it choose. This idea is not merely metaphorical. It is built into the mathematics of quantum mechanics. The wave function, a mathematical description of all the possible states of a particle, evolves smoothly according to the Schrödinger equation, but when measured, the wave function abruptly collapses into one of its possible values. The transition from possibility to reality is discontinuous and deeply mysterious. It is not clear why measurement should cause this collapse, or even what counts as a measurement. Does it require a conscious observer, a physical detector, an irreversible record? Physicists have proposed many interpretations of this paradox. The Copenhagen interpretation, widely taught and historically dominant, says that particles do not have definite properties until measured. Reality is probabilistic, and the observer plays a central role in defining the outcome. But this invites philosophical unease. Are we saying that reality depends on being looked at? That, in the absence of observation, the world exists only as a blur of probability? Alternative interpretations offer different perspectives. The many worlds interpretation suggests that every possible outcome actually occurs, but in separate branching universes. In this view, the electron goes through both slits, but we observe only one version of reality because we ourselves split into branches, each experiencing a different result. There is no wave function collapse, only divergence. Another view, known as pilot wave theory or de Broglie-Bohm theory, suggests that particles do have definite paths, but are guided by an invisible wave that encodes all possible outcomes. In this model, the mystery lies not in measurement, but in the hidden variables that influence the particle's motion. More recent experiments have pushed the boundaries of the paradox even further. In delayed choice experiments, scientists wait until after the particle has passed the slits to decide whether to measure which slit it went through. Astonishingly, the result still depends on the measurement choice, even though it occurs after the particle's journey. It's as if the particle's past is rewritten based on how we observe it in the present. Time itself seems to blur. Cause and effect begin to wobble. What does the double-slit experiment tell us, then, about the nature of reality? At the very least, it reveals that particles are not as localized or definite as they seem. They behave more like tendencies than things, and it shows that observation, in some deep and subtle way, matters. The universe at the quantum level does not unfold as a predetermined sequence of events. It unfolds as a dance of probabilities, collapsing into form only when attention is cast upon it. This has led some thinkers to speculate about the role of consciousness in the quantum realm. Could awareness itself be the catalyst that brings reality into being? Others reject this view, insisting that detectors or any irreversible interaction with the environment suffice. Still, the question remains open, and the paradox continues to challenge our understanding. The double-slit experiment is more than a demonstration of quantum weirdness. It is a mirror that reflects the limits of our assumptions. We believe that objects must be in one place at a time, that paths are singular, that cause and effect follow a linear order. But nature whispers otherwise. At the smallest scales, it seems, reality is not composed of definite answers, but of questions waiting to be asked, and the form of the question shapes the form of the answer. So the next time you think of an electron passing through a slit, remember this: until you look, it may be everywhere at once, both here and there, both now and later, both known and unknowable. The world beneath the surface is a realm not of things, but of possibilities, and in that realm, your gaze is not passive, it is creative. You are not simply observing the universe, you are helping to shape the outcome. Faint young sun paradox. Billions of years ago, long before the first trees took root or animals walked the earth, our young planet was already covered in liquid water. Evidence from ancient rocks, fossils, and geological structures tells us that rivers flowed, oceans lapped against primitive shores, and microbial life flourished beneath the waves. Yet there's something profoundly puzzling about this picture. At the time, the sun was much fainter than it is today, emitting only about 70 to 75% of its current energy output. According to basic physics, that lower solar output should have left Earth frozen solid, locked in a deep global ice age. But it wasn't. Somehow, against all expectations, early Earth remained warm enough to support liquid water and life. This contradiction between the young sun's feeble energy and the planet's relatively mild climate is known as the faint young sun paradox, and it remains one of the most intriguing and persistent mysteries in planetary science. The paradox arises from well-understood principles of stellar evolution. Like all stars, our sun is a fusion engine. Over time, as hydrogen atoms in the core are converted into helium through nuclear fusion, the core gradually contracts and heats up. This process increases the rate of fusion and leads to a brighter, more energetic star. Models of stellar aging suggest that 4 billion years ago, during the Archean eon, the sun's luminosity was about 30% less than it is today. That decrease in sunlight would have had a dramatic effect on Earth's surface temperature. All else being equal, a cooler sun would have resulted in an average global temperature far below the freezing point of water. Oceans would have been sealed beneath thick layers of ice, and the emergence of life as we know it would have been delayed or prevented entirely. Yet geological evidence tells a different story. Some of the oldest sedimentary rocks on Earth show ripple marks and features formed by flowing water. Ancient stromatolites, layered structures built by microbial communities, suggest the presence of thriving aquatic ecosystems. Even zircon crystals from as far back as 4.4 billion years ago contain isotopic signatures consistent with the presence of liquid water. These findings point to a planet that, while not tropical, was certainly not frozen. The early Earth was habitable, temperate, and surprisingly warm for a world orbiting a dim young star. To resolve this contradiction, scientists have explored a variety of hypotheses, each attempting to account for the missing heat. One of the most widely considered explanations involves Earth's atmosphere. If the early atmosphere contained higher levels of greenhouse gases, particularly carbon dioxide, CO2, and methane, CH4, it could have trapped more heat and offset the reduced solar input. Greenhouse gases work by absorbing infrared radiation emitted by the planet's surface and re-radiating it back, warming the lower atmosphere and surface. If early Earth had thick clouds of carbon dioxide or methane-rich haze, the greenhouse effect could have been significantly stronger than it is today. This idea is supported by some geochemical evidence. Certain rock formations and isotopic patterns suggest that volcanic activity was more intense in Earth's early history, releasing vast quantities of carbon dioxide into the atmosphere. With fewer land plants and slower weathering processes to draw down CO2, these gases may have lingered longer, maintaining a warmer climate. Additionally, early microbes called methanogens, primitive organisms that produce methane as a byproduct, may have contributed to high methane levels. Since methane is an even more potent greenhouse gas than carbon dioxide, its presence in a relatively oxygen-free early atmosphere could have had a major warming effect. But the greenhouse solution is not without complications. For one, if CO2 levels were extremely high, we would expect to see certain mineral signatures in ancient soils and rocks, signatures that are not always present. Similarly, high methane concentrations can lead to the formation of organic hazes that block sunlight, potentially cooling the planet. Balancing these opposing effects has proven difficult in climate models, and the exact composition of the early atmosphere remains uncertain. Some researchers have suggested that other gases, like ammonia, could have played a role, but ammonia is quickly broken down by ultraviolet radiation and would not persist long unless shielded by a thick haze or magnetic field. Another possible contributor to early Earth's warmth is the planet's albedo, the fraction of sunlight that is reflected back into space. A lower albedo means more solar energy is absorbed, contributing to warming. In the Archean era, Earth may have had less landmass and more open ocean, which absorbs more sunlight than continents or ice. Additionally, cloud cover and ice distribution could have been different, affecting how much energy was retained. Some climate models suggest that even a modest reduction in planetary albedo could help bridge the temperature gap left by the faint sun. Yet another theory points to the potential influence of geothermal heat. The young Earth was more geologically active, with a hotter interior and more frequent volcanic eruptions. This internal heat could have contributed modestly to surface temperatures, particularly in the deep oceans where hydrothermal vents could create localized warm environments. While geothermal energy alone could not maintain global warmth, it might have played a supporting role in keeping key regions above freezing, providing sanctuaries for early life. A more speculative idea involves changes to the sun's behavior itself. Could the sun have been more active in its youth, emitting bursts of radiation or solar wind that affected Earth's climate? While the sun likely had a more intense solar wind and magnetic activity, these phenomena tend to strip atmospheres rather than warm planets. Nonetheless, some researchers continue to explore whether solar variability or unknown stellar processes could help resolve the paradox. In recent years, scientists have also turned to advanced climate modeling and computer simulations, trying to recreate early Earth's environment in detail. These models incorporate data on atmospheric composition, volcanic activity, ocean circulation, cloud formation, and planetary tilt. While no single factor fully solves the faint young sun paradox, a combination of moderate greenhouse effects, lower albedo, and feedback mechanisms appears capable of producing a habitable climate even under a dimmer sun. The answer may lie not in a single explanation, but in the subtle interplay of many contributing factors. Beyond Earth. The faint young sun paradox has implications for the search for life elsewhere in the universe. If early Earth remained warm under a weaker sun, could similar processes occur on exoplanets orbiting faint stars? Could planets once dismissed as too cold for life actually harbor warmth beneath dense atmospheres or protective clouds? Understanding how early Earth escaped a frozen fate may expand our definition of the habitable zone and reshape how we search for biosignatures across the galaxy. Philosophically, the paradox also reminds us of the fine-tuned balance required for habitability. A slight change in solar output, atmospheric chemistry, or planetary reflectivity could have tipped early Earth into a global ice age, and yet, somehow, life emerged and persisted. The story of the faint young sun paradox is not just a scientific puzzle, it is a testament to the resilience of life and the intricate harmony of cosmic forces. It invites us to consider how delicate and miraculous our planet's early environment may have been, and how many variables had to align just so for us to exist today. The paradox remains partially unsolved, a reminder that the early Earth still holds secrets locked in ancient rocks and buried beneath forgotten oceans. As we continue to investigate its climate history, we gain not only a clearer picture of our past, but also a deeper sense of the dynamic, ever-changing nature of our planet. And perhaps, in the echoes of a fainter sun, we can hear the quiet resilience of a world that found a way to stay warm, to stay wet, and to awaken life long before the light grew strong. Black hole information paradox. Among the most enigmatic and fearsome objects in the universe, black holes stand as dark sentinels at the edge of known physics. Born from the catastrophic collapse of massive stars, they warp space-time so severely that nothing, not even light, can escape their grasp. Their boundaries, the event horizons, represent points of no return, places where the very fabric of reality is torn beyond recognition. Yet, as mysterious as black holes are, it was the clash between their nature and the principles of quantum mechanics that gave rise to one of the greatest puzzles in modern science, the black hole information paradox. It asks a simple but profound question. When something falls into a black hole, is the information about its original state lost forever? And if so, does this violate the very laws that govern the universe at its most fundamental level? The paradox arises from a collision between two pillars of physics. On one side stands general relativity, Albert Einstein's masterful description of gravity and space-time, which predicts the formation and behavior of black holes with astonishing accuracy. According to relativity, whatever crosses the event horizon is cut off from the rest of the universe. The details of what falls in, whether it is a star, a planet, or a teacup, seem to be irrelevant. All black holes are defined by just a few properties: their mass, their charge, and their spin. This simplicity gave rise to the famous saying, "Black holes have no hair." In other words, all the rich information about the things that created the black hole or fell into it is erased from the universe, leaving behind only bland, featureless remnants. But on the other side stands quantum mechanics, the deeply successful theory that describes the behavior of matter and energy at the smallest scales. In quantum theory, information is sacred. The evolution of any closed quantum system must be reversible, meaning that, at least in principle, the system's earlier state can always be reconstructed from its current state. Information cannot be destroyed, only transformed. The past is encoded in the present, and the universe keeps perfect track of everything that happens within it. This principle is not a minor detail. It is woven into the very mathematics that describe quantum processes. Thus, the paradox emerges. If black holes destroy information by swallowing it beyond the event horizon, then they violate the fundamental laws of quantum mechanics. If they don't destroy information, then somehow that information must be preserved or released, even as the black hole devours matter and evaporates away. But how could that be? How could information trapped beyond an event horizon ever escape? The puzzle deepened in the 1970s when Stephen Hawking made a groundbreaking discovery. Black holes are not completely black. Due to quantum effects near the event horizon, black holes can emit radiation, now known as Hawking radiation. This radiation arises from the spontaneous creation of particle-antiparticle pairs at the edge of the black hole. One particle falls in, while the other escapes, carrying away a tiny bit of energy. Over unimaginable timescales, this process causes black holes to lose mass and eventually evaporate completely. At first, this seemed like a beautiful synthesis of quantum theory and general relativity, but a closer look revealed a fatal flaw. Hawking radiation is completely random. It carries no information about the material that originally formed the black hole or about the things it has consumed. It is pure, featureless heat, like the radiation from a burning log, but without any way to reconstruct the log from the ashes. If the black hole evaporates entirely and the only trace left behind is this featureless radiation, then the information about what fell in has vanished. And that is something quantum mechanics says cannot happen. Thus, the black hole information paradox was born. It posed a stark dilemma: either accept that information can be destroyed, breaking quantum theory, or find some new physics that preserves information in ways we don't yet understand. Neither option is comfortable. Over the decades, physicists have proposed numerous ideas to resolve the paradox, each more ingenious and often more bewildering than the last. One proposal suggests that information is somehow preserved in the Hawking radiation itself, albeit in a subtle, highly scrambled form. If true, then black holes act not as information destroyers, but as information scramblers, messy, chaotic processors that ultimately radiate information back into the universe, just extremely slowly and in ways almost impossible to decode. In this view, no laws of quantum mechanics are broken, but retrieving the original information would be practically hopeless, like trying to reconstruct a book after burning it to ash, and then scattering the ash across a galaxy. Another idea is the concept of black hole complementarity. It proposes that information is both reflected back at the event horizon and passes through it, but never in a way that allows an observer to witness both. From outside, an infalling object appears to smear out over the event horizon and gradually leak its information back into the Hawking radiation. From the infalling object's own perspective, however, it crosses the horizon without incident. No observer sees a violation of physics, and quantum theory remains intact. Reality, it seems, might depend on the observer's point of view. More radically, the firewall hypothesis suggests that the event horizon is not a smooth, gentle boundary, but a searing wall of high-energy particles. Anything trying to cross it would be instantly incinerated. This fiery boundary could somehow preserve information by preventing it from being lost inside the black hole. However, this idea contradicts the equivalence principle of general relativity, which states that free-falling observers should experience nothing unusual at the event horizon. Thus, while firewalls could solve the information paradox, they would tear down one of the central pillars of Einstein's theory. Still others propose that information is encoded on the two-dimensional surface of the event horizon itself, a notion related to the holographic principle. In this view, the three-dimensional information about everything that falls into a black hole is somehow stored on its two-dimensional boundary, like a cosmic hard drive. As the black hole evaporates, this information could be slowly released, preserving quantum theory's demands. The holographic principle has found support in other areas of theoretical physics, particularly in the study of quantum gravity, and hints at a profound relationship between information, space-time, and reality itself. Despite decades of work, the black hole information paradox remains unresolved. It sits at the intersection of gravity, quantum mechanics, and thermodynamics, hinting that a deeper, unified theory of nature may lie beyond our current understanding. Some believe that a complete theory of quantum gravity, perhaps string theory or loop quantum gravity, will eventually reconcile the paradox. Others suspect that the solution may involve a radical rethinking of space, time, and causality themselves. What makes the paradox so haunting is that it touches on fundamental questions about reality. Is information truly indestructible? Does the universe obey a deeper order that we have yet to uncover? Or is there a place, hidden behind the event horizons of black holes, where the rules break down and knowledge is lost forever? Until we find the answer, black holes will remain not just astronomical objects, but philosophical ones, cosmic riddles wrapped in darkness, whispering secrets we are only beginning to hear. And so the paradox endures, like a beacon in the darkness, guiding physicists to probe deeper into the nature of reality. For at the heart of the black hole information paradox lies the promise that by understanding what happens to information at the edge of existence, we might finally glimpse the deeper architecture of the universe itself. Missing dwarf galaxies paradox. Across the vast silent reaches of space, galaxies form the grand architecture of the cosmos. Enormous spirals like the Milky Way, glowing ellipticals, and scattered irregulars, all woven into a colossal web stretching across the universe. Yet, in the great tapestry of cosmic structure, there lies a curious absence, a silence where we expected to find abundance. According to our best cosmological models, there should be a teeming multitude of small galaxies, dwarf galaxies, scattered around every major galaxy like satellites around a planet. But when we look to the sky with our most sensitive instruments, we find far fewer of these faint companions than theory predicts. This gap between prediction and observation is known as the missing dwarf galaxies paradox, and it raises unsettling questions about our understanding of the universe's invisible scaffolding. Dark matter, cosmic evolution, and the forces that shape galaxies themselves. The story begins with the cold, dark matter model, the cornerstone of modern cosmology. In this model, most of the matter in the universe is not the ordinary atoms that make up stars, planets, and people. Instead, it is dark matter, a mysterious, invisible substance that interacts gravitationally but not through light or other electromagnetic forces. Dark matter provides the gravitational glue that holds galaxies together, prevents them from flying apart, and seeds the formation of cosmic structures after the Big Bang. According to computer simulations based on the CDM model, galaxies like the Milky Way should be surrounded by hundreds, even thousands of smaller dark matter clumps, many of which should have gathered enough gas to form dwarf galaxies. But when astronomers actually catalog the dwarf galaxies orbiting the Milky Way and other large galaxies, the numbers fall dramatically short. Instead of hundreds or thousands, we observe only a few dozen. The same scarcity appears around other galaxies. Even with deep surveys, sensitive enough to detect faint and diffuse objects, the expected dwarf galaxy swarms simply aren't there. Where are they hiding, or are they missing altogether? This discrepancy challenges one of the fundamental predictions of the cold dark matter model. If the model is correct, then these dark matter subhollows, the seeds of dwarf galaxies, should be everywhere. Their absence suggests either that the model needs revision, or that something is preventing these clumps from lighting up with stars, making them effectively invisible to our telescopes. Thus, the paradox unfolds. The universe should be crawling with tiny galaxies, yet we see only a handful. Several possible explanations have been proposed to bridge the gap between theory and observation. One idea is that many of the predicted dwarf galaxies exist but remain dark, filled with dark matter but almost entirely devoid of stars. If these sub-halos failed to accrete enough gas during their formation, or if early processes stripped away their gas before stars could form, then they would be effectively invisible. Like ghosts haunting the halos of larger galaxies, these dark dwarfs would exert gravitational influence but emit little to no light. Astrophysicists suspect that processes in the early universe may have played a critical role. After the Big Bang, the universe was filled with a searing high-energy plasma. As it cooled, neutral hydrogen formed, allowing the first stars and galaxies to ignite. However, when the first massive stars exploded as supernovae and early black holes blazed as quasars, they flooded the universe with high-energy radiation. This radiation could have heated and dispersed the gas in small dark matter halos, preventing star formation altogether. Thus, many of the potential dwarf galaxies may have been sterilized before they ever had a chance to shine. Another contributing factor could be the harsh internal environments of these fledgling galaxies. Even if some gas remained after reionization, the gravitational pull of small dark matter halos might have been too weak to hold on to it. Supernova explosions within the first generations of stars could have blown the remaining gas away, halting further star formation and leaving behind dim, barren remnants. These failed galaxies, sometimes called ultra-faint dwarfs or dark galaxies, would be nearly impossible to detect with current technology. Some researchers have also suggested that our understanding of dark matter itself may need refinement. Perhaps dark matter doesn't behave exactly as the cold dark matter model predicts. Alternative theories like warm dark matter propose particles with slightly higher velocities than their cold counterparts. This subtle change would suppress the formation of small-scale structures, naturally leading to fewer dwarf galaxies without requiring them to be invisible. Other exotic ideas, such as self-interacting dark matter, posit that dark matter particles could collide and redistribute energy, affecting how small halos form and survive. Another possibility is observational bias. Dwarf galaxies are faint, diffuse, and often extremely difficult to detect, especially if they lie far from their host galaxy or against a crowded backdrop of the Milky Way. As telescope technology improves, we have indeed discovered more ultra-faint dwarf galaxies in recent years, suggesting that some of the missing population may simply be hidden beyond our current reach. Upcoming surveys like the Vera C. Rubin Observatory's Legacy Survey of Space and Time, LSST, are expected to uncover many more faint galaxies, potentially easing the tension between theory and observation. Yet even if more dwarf galaxies are found, the paradox will likely persist in some form. The sheer magnitude of the gap between predicted and observed numbers suggests that detection limits alone cannot fully account for the discrepancy. Some combination of astrophysical processes and new physics may be at work, reshaping the formation and survival of small galaxies in ways we do not yet fully understand. The missing dwarf galaxies paradox also touches on broader questions about the nature of cosmic structure. Dwarf galaxies are not just curiosities, they are vital pieces of the puzzle. They serve as laboratories for understanding dark matter, as relics of the early universe, and as building blocks of larger galaxies. If we misunderstand the population of dwarfs, we may misunderstand the entire history of galactic evolution. In a broader philosophical sense, the paradox reminds us that absence can be as revealing as presence. What we do not see can shape our understanding just as powerfully as what we do. The missing dwarfs challenge our theories, pushing us to refine our models, question our assumptions, and explore new possibilities. They hint that the universe still holds secrets close, waiting for us to develop sharper eyes and deeper insights. In the coming years, with new instruments, more sensitive detectors, and deeper surveys, we may finally begin to fill in the missing pieces of this cosmic puzzle. We may discover hidden populations of dark galaxies, find subtle imprints of missing dwarfs through their gravitational effects, or uncover new physics that reshapes our view of the universe's invisible scaffolding. The solution to the missing dwarf galaxies paradox will not just tell us where the missing galaxies are. It will illuminate the forces that govern the birth, growth, and death of galaxies themselves. Until then, we are left with a universe that seems quieter than it should be, a sky with fewer companions than our models predict. But in that quietness, in that unexpected stillness lies a mystery, a doorway to deeper understanding, and a reminder that even in the age of powerful telescopes and sophisticated simulations, the cosmos still holds many of its oldest truths just out of reach, in the faint shadows between the stars. Rotation of dwarf galaxies paradox. In the far reaches of space, beyond the bright spirals and majestic ellipticals that define the cosmic landscape, there exist small, dim galaxies, dwarf galaxies, that orbit their larger counterparts like loyal companions. These tiny galactic systems, containing just a fraction of the stars found in giants like the Milky Way, might seem insignificant at first glance. Yet hidden in their slow, quiet spin is a paradox that has stirred some of the most profound debates in modern astrophysics. When scientists began to measure how these dwarf galaxies rotate, they found something unexpected, something that didn't fit with the predictions of Newtonian gravity, or even with the vast scaffolding of dark matter that underlies our current cosmological models. This inconsistency is known as the rotation of dwarf galaxies paradox, and it challenges our most basic understanding of how gravity works on the smallest galactic scales. To understand this paradox, we must first revisit what happens in larger galaxies. In a spiral galaxy like the Milky Way, stars near the center orbit quickly, as expected due to the concentration of mass in the core. But as we move further from the center, the stars continue to orbit at nearly the same speed, rather than slowing down as Newton's laws would suggest if only visible matter were present. This anomaly led scientists to propose the existence of dark matter, an unseen form of mass that adds the necessary gravitational pull to keep those outer stars moving so rapidly. The theory of dark matter has since become a cornerstone of modern cosmology, helping explain not just galactic rotation curves, but the large-scale structure of the universe itself. So naturally, when astronomers turn their attention to dwarf galaxies, systems that are much less massive and composed of fewer stars, they expected to see similar evidence of dark matter at work. And in many ways, they did. The stars in these galaxies often move too fast to be held together by the visible matter alone, suggesting the presence of an invisible gravitational influence. But here is where the paradox begins to emerge. The rotation curves of many dwarf galaxies do not just imply the existence of dark matter, they follow patterns that are strangely universal. Regardless of size, composition, or environment, many of these galaxies exhibit the same unexpected relationship between their visible mass and rotational speeds. This regularity suggests a deeper, underlying law, something that Newtonian gravity, even with dark matter included, struggles to fully explain. One particularly striking observation is that dwarf galaxies appear to defy the expected scatter in their dynamics. In a universe filled with chaotic, random events, mergers, feedback, interactions, supernovae, we would expect a wide range of outcomes in how dwarf galaxies rotate, but the data shows a surprising uniformity. When plotted on a graph comparing the acceleration due to gravity and the acceleration inferred from rotation, dwarf galaxies fall neatly along a specific curve. This relation, known as the radial acceleration relation, RAR, is so precise that it has led some scientists to question whether our understanding of gravity itself is incomplete. Enter modified Newtonian dynamics, or MOND. First proposed in the 1980s by physicist Mordechai Milgram, MOND suggests that at very low accelerations, such as those found in dwarf galaxies, Newton's laws of motion break down and must be replaced with a modified version. According to MOND, there is a threshold below which gravity does not behave as Newton or Einstein predicted, and instead follows a different rule, one that naturally produces the flat rotation curves observed in galaxies without invoking dark matter. For large, high-acceleration systems like the Milky Way, MOND reduces to Newtonian gravity, but in the low-acceleration regime of dwarf galaxies, it predicts the behavior we actually observe. MOND has had a controversial history. Many physicists view it as a useful but incomplete approximation, a patch rather than a full theory of gravity. Critics point out that while MOND explains galactic rotation curves well, it struggles to account for phenomena on larger cosmic scales, such as galaxy clusters and the cosmic microwave background, where dark matter still fits better. Yet the precision with which MOND predicts the behavior of dwarf galaxies, particularly their rotation without apparent scatter, remains deeply compelling. It suggests that either MOND is tapping into a deeper truth, or that the standard model of dark matter and gravity is missing something fundamental. Adding further complexity is the discovery that satellite dwarf galaxies tend to arrange themselves in thin, coherent planes around their host galaxies. For example, many of the Milky Way's dwarf galaxies orbit in a flat, disk-like structure, rather than being randomly distributed in 3 dimensions as simulations of dark matter would suggest. This behavior is difficult to reconcile with the expected distribution of dark matter subhalos, which should be more spherical and chaotic. Such alignments hint at dynamics that are not easily explained by standard cosmology, reinforcing the sense that our gravitational model may require revision or that some hidden structure is influencing their motion. Some astrophysicists argue that the paradox may not lie in the laws of gravity at all, but in the way galaxies form and evolve. Feedback processes from star formation, such as supernova explosions and stellar winds, can blow gas out of galaxies and reshape their dark matter profiles. If these processes are more finely tuned than previously thought, they might create the illusion of a modified gravitational law. But simulating such precise feedback mechanisms is challenging, and even the most sophisticated models still struggle to reproduce the uniformity observed in dwarf galaxy rotation. Others suggest that the dark matter itself may not be as passive as once believed. Instead of being cold and collisionless, dark matter might interact weakly with itself or with normal matter, redistributing energy and smoothing out irregularities. This self-interacting dark matter could lead to more uniform internal structures in dwarf galaxies, potentially explaining the observed rotation curves without changing gravity. However, such models are still speculative and lack definitive observational support. At its core, the rotation of dwarf galaxies paradox is not just about tiny galaxies behaving oddly, it's about the foundation of physics itself. It forces us to ask whether the laws we take for granted truly apply on all scales and in all regimes. Is gravity universal, or does it bend and shift under conditions we have not yet fully grasped? Do unseen particles shape the cosmos, or does the universe respond to mass and motion in ways we have yet to understand? Perhaps, as technology advances and new surveys map more of the faintest galaxies in the sky, we will find clarity. Projects like the Vera C. Rubin Observatory promise to reveal thousands of new dwarf galaxies, offering a broader sample to test these puzzling trends. As we gather more data, patterns may emerge, pointing the way toward new physics, or confirming the theories we already hold. Until then, the paradox remains, a quiet rebellion against our expectations, a small voice from the outskirts of the universe asking us to look again, think deeper, and question what we thought we knew. Dwarf galaxies, though tiny and dim, may hold the keys to cosmic truths far greater than their size suggests. Like ancient scrolls written in a forgotten dialect, they speak in the language of rotation and gravity, whispering that the universe may not be as settled or as simple as we once believed. The paradox endures not because it defies explanation, but because it defies complacency. It reminds us that even in the shadows, even at the edges of things, profound mysteries still spin silently in the dark. Dark Forest Paradox. The universe stretches outward in all directions, an unfathomable ocean of stars, planets, and galaxies scattered across the vastness of space. Every star we see could be home to planets, and many of those planets might harbor life. Yet, despite the overwhelming numbers, despite decades of listening, searching, and hoping, the sky remains eerily silent. We hear no transmissions, see no signs, receive no messages from the countless worlds that must exist beyond our own. This silence is the essence of the Fermi paradox. If life is common, where is everyone? One chilling answer emerges from the imagination and logic of science fiction and serious thinkers alike: the Dark Forest Paradox. It suggests that the universe is silent not because civilizations are rare, but because they are terrified. In a cosmos where every encounter could mean destruction, the safest strategy is to remain hidden, silent, and invisible. The name Dark Forest comes from a metaphor. Imagine the universe as a dark, dense forest at night. In this forest, every civilization is a silent hunter, creeping through the undergrowth, aware that others might be nearby, but never certain. Each hunter knows that every other hunter is armed, that survival depends on avoiding detection, and that any noise could bring fatal attention. In such a place, to announce oneself would be an act of supreme folly, a beacon that says, "Here I am," to every potential threat. And so, in this cosmic forest, Civilizations stay quiet, not because they are unfriendly, but because they are rational, because they understand the ultimate stakes of being seen. This idea was explored in haunting depth by Chinese science fiction author Liu Cixin in his novel The Dark Forest, but its roots run deeper, tapping into the brutal logic of survival in an uncertain universe. In the absence of trust, and with no way to guarantee the intentions of others, the safest assumption is that others might be hostile. Worse, by the time you confirm their intentions, it might be too late. Technology advances exponentially, and a civilization that is peaceful today could become a threat tomorrow. In a universe where the cost of being wrong is extinction, the incentive to preemptively strike, or at least to remain hidden, is overwhelming. The Dark Forest paradox challenges one of the most optimistic assumptions behind projects like SETI, the search for extraterrestrial intelligence. These efforts are built on the idea that advanced civilizations would want to communicate, to share knowledge, to announce their presence, as we long to announce ours. Yet the Dark Forest suggests the opposite. It argues that any civilization smart enough to survive would understand that signaling its existence could bring ruin. They would know that discretion is the better part of valor. They would choose silence, concealment, and camouflage over the risk of reaching out. The quiet sky is not an empty sky, it is a tense, silent standoff across light years. There are deep and unsettling reasons why this logic might dominate cosmic behavior. First is the problem of mutual ignorance. No civilization can know the true intentions or capabilities of another. Distance offers no safety. If a civilization can detect us, it might be able to launch weapons at near light speed, giving us little or no warning. And unlike in human affairs, there is no third party to mediate, no universal law to enforce peace between stars. Each civilization must make its own decisions in isolation, gambling its survival on assumptions it cannot verify. Second is the problem of technological unpredictability. The gap between civilizations could be vast, not just in years, but in the power of their technology. A civilization just a few hundred years ahead of us might wield forces we cannot even imagine. To them, we could be as vulnerable as ants are to humans. And even if they are peaceful now, the possibility that they could change, that they could one day pose a threat, remains. In the long view of cosmic time, potential threats cannot be ignored simply because they are peaceful in the present. Third is the principle of asymmetrical risk. If two civilizations encounter each other and both are peaceful, great possibilities could unfold. Shared knowledge, mutual growth, companionship across the stars. But if even one is hostile, the peaceful civilization risks annihilation. The downside of trusting is far greater than the upside of friendship. Under these conditions, prudence dictates suspicion. It is safer to assume the worst, to hide, to stay quiet, and to prepare for the worst, rather than to hope for the best. In this light, broadcasting our presence into the cosmos as we have done with radio waves, spacecraft like Voyager, and deliberate signals aimed at nearby stars might be seen not as a bold act of exploration, but as a dangerous gamble. Some thinkers argue that we have been reckless, shouting into the cosmic night without understanding who might be listening. Others believe it is already too late, that our planet's atmospheric signatures, oxygen, radio waves, industrial pollution have already betrayed us to any civilization capable of detecting them. Yet the Dark Forest paradox also raises a profound psychological question. Would a truly advanced civilization still be governed by fear and survival instincts? Would they not, having mastered their own internal conflicts, have moved beyond the need for suspicion? Perhaps they would see themselves as stewards of life, protectors rather than predators. But that is a hopeful assumption, not a logical one. Evolution favors survival, and survival often favors caution, mistrust, and defensive aggression. Even if a civilization overcame these tendencies internally, it could not be sure that others had done the same. And so, the silence remains. There are possible counterarguments. Perhaps civilizations are so widely separated in space and time that encounters are vanishingly rare. making the dark forest more empty than deadly. Perhaps technological civilizations tend to self-destruct before reaching the stars, leaving few to hide or hunt. Or perhaps there are civilizations out there who have found ways to communicate safely through coded signals, quantum entanglement, or other means we have yet to understand. Still, the dark forest remains a powerful metaphor for the silence of the cosmos. It paints a picture of a universe teeming not with absence, but with fear. A universe where lights are hidden, fires are banked low, and every world watches the stars with wary eyes, choosing survival over contact, safety over curiosity. It is a sobering vision, one that transforms the night sky from an inviting frontier into a place of quiet, invisible tension. For humanity, the dark forest paradox forces hard questions about our own future. Should we continue trying to make contact, or should we fall silent ourselves? Should we pour resources into hiding Earth's signature, masking our radio emissions, camouflaging our atmospheric markers, or accept the risks of openness? Should we assume that any visitors will come in peace, or prepare for less benign possibilities? These are not merely theoretical questions. They are choices that could shape the destiny of our species. The dark forest paradox reminds us that while hope and wonder are vital to exploration, so too are caution and humility. The universe may be vast, ancient, and silent, not because it is empty, but because it is full of civilizations that have learned, through long experience or instinctive prudence, that survival sometimes demands silence. As we peer deeper into the cosmos, we may find that the greatest mystery is not why the stars are silent, but why we ever expected them to sing. Quantum entanglement paradox. At the very heart of quantum mechanics lies a phenomenon so strange, so unsettling, that even Albert Einstein famously derided it as spooky action at a distance. This phenomenon is known as quantum entanglement, and it stands as one of the most profound paradoxes in all of physics. It describes a situation where two or more particles become linked in such a way that the state of one immediately affects the state of the other, no matter how far apart they may be, across a room, across a galaxy, across the universe itself. In the entangled world, distance becomes irrelevant. Measurement on one particle seems to instantaneously influence the outcome for the other, defying the speed limit imposed by light and challenging our deepest intuitions about how reality should behave. Quantum entanglement arises naturally from the mathematics of quantum mechanics. When particles interact in certain ways, they can become part of a shared quantum state. Their properties, such as spin, polarization, or momentum, become correlated so completely that they can no longer be described independently of each other. Instead, the two particles must be treated as a single, unified system, even if they later move far apart. If you measure one, you instantly know the state of the other. But here is where the paradox deepens. According to quantum theory, the properties of each particle are not determined until they are measured. They exist in a superposition of all possible states. Only upon observation do the possibilities collapse into a definite outcome. So when we measure one particle and instantly learn the state of its partner, it appears that information has traveled faster than light, something Einstein's theory of relativity forbids. This tension between quantum mechanics and relativity sparked fierce debate among the founders of modern physics. Einstein, together with colleagues Boris Podolsky and Nathan Rosen, formulated what became known as the EPR paradox. In their 1935 paper, they argued that if quantum mechanics were correct, it must be incomplete. They believed there must be hidden variables, unknown factors governing the behavior of particles that would restore determinism and locality to physics. In other words, they hoped that reality was fundamentally classical at its core, obeying cause and effect within the boundaries set by the speed of light. But in the 1960s, physicist John Bell developed a theoretical test that could distinguish between the predictions of quantum mechanics and those of any local hidden variable theory. Bell's inequalities provided a way to experimentally check whether entangled particles behaved as if they carried pre-existing information about their states, or whether their outcomes were truly determined only upon measurement. Subsequent experiments, beginning in the 1970s and growing increasingly sophisticated over the decades, have consistently supported the quantum view. Entangled particles violate Bell's inequalities, demonstrating correlations that cannot be explained by any local hidden variables. Reality, it seems, is non-local. Quantum mechanics is not just a strange model, it describes how the universe actually behaves. Yet this raises profound and unsettling questions. If entanglement is real, and the experiments leave little doubt that it is, then how do we reconcile it with the prohibition against faster-than-light communication? Quantum theory sidesteps this problem by insisting that while the correlations between entangled particles are instantaneous, they cannot be used to transmit information faster than light. You cannot use entanglement to send a message or signal. The results of measurements are random, and only when compared later do the correlations emerge. Thus, causality remains intact, even if the underlying connection defies classical understanding. Still, the paradox persists. What is the mechanism behind entanglement? How can one particle know the outcome of a measurement performed light years away? Is space itself an illusion, with entangled particles existing in a deeper underlying unity that transcends distance? Some interpretations of quantum mechanics, such as the many worlds interpretation, avoid the issue by positing that all possible outcomes occur each in its own branching universe. In this view, entanglement reflects the structure of the multiverse rather than a spooky action within our own. Other interpretations, like pilot wave theory, maintain that non-local influences guide particles behind the scenes, accepting faster-than-light effects, but denying that they can be used for communication. Recent experiments have pushed entanglement to ever greater extremes. Photons have been entangled across distances of hundreds of kilometers, and plans are underway to test entanglement between Earth and satellites in orbit. Each success strengthens the reality of entanglement and deepens the mystery. Some researchers are even exploring the possibility that entanglement is not just a curiosity of quantum mechanics, but a fundamental feature of space-time itself. Theorists like Juan Maldacena and Leonard Susskind have proposed that quantum entanglement and the geometry of space-time are intimately connected, a concept encapsulated in the slogan ER equals EPR. This bold idea suggests that entangled particles are connected by microscopic wormholes, tiny bridges in space-time, although no information can pass through them. If true, then the fabric of reality might be woven together by countless invisible threads of entanglement, binding the cosmos into a unified whole. The technological implications of entanglement are equally staggering. Quantum entanglement is the foundation for emerging fields like quantum computing, where entangled qubits can perform complex calculations at speeds unimaginable for classical computers. It is also the basis for quantum cryptography, promising communication channels so secure that eavesdropping would be instantly detectable. In quantum teleportation experiments, entanglement enables the transfer of quantum states from one particle to another across distances, hinting at future technologies that could reshape our understanding of communication and information. And yet, despite its experimental successes and technological promise, the essence of entanglement remains elusive. It forces us to confront a universe where separateness is an illusion, where particles can be intimately linked across vast gulfs of space, and where observation itself seems to weave the threads of reality. It invites us to imagine that the cosmos is not a collection of isolated objects scattered through emptiness, but a vast, interconnected web, trembling with unseen connections that bind the smallest scales to the largest. The quantum entanglement paradox is not simply about particles influencing each other across distance. It is about the nature of reality itself, about whether the world we experience is a patchwork of local interactions or a seamless, holistic fabric. It challenges our deepest intuitions about cause and effect, about separation and connection, about the limits of knowledge and the structure of existence. It reminds us that beneath the familiar surface of things, the universe remains profoundly, beautifully, and unsettlingly strange. As we continue to explore the quantum world, we may find that entanglement is not just a feature of the microscopic realm, but a key to understanding the cosmos at every scale. And perhaps, in the eerie, silent dance of entangled particles, we will glimpse a deeper truth, that distance is an illusion, that division is a myth, and that in the ultimate fabric of reality, everything is connected. Local realism paradox. Throughout much of human history, our understanding of the world has rested on two bedrock assumptions: that objects have properties independent of observation, and that influences cannot travel faster than light. These two principles, known together as local realism, form the foundation not just of classical physics, but of our everyday sense of how the world works. Locality tells us that objects can only affect each other through interactions that occur within their light cones, at or below the speed of light. Realism tells us that the properties of objects exist independently of whether they are measured or observed. But, with the rise of quantum mechanics in the 20th century, these comforting pillars began to shake. And today, experiments have pushed us to a startling conclusion. The universe may not be local, it may not be realistic, or perhaps it is neither. This profound tension is known as the local realism paradox, and it invites us to rethink the very nature of existence. The seeds of this paradox were sown with the famous Einstein-Podolsky-Rosen paper of 1935. Einstein, deeply troubled by the strange implications of quantum mechanics, argued that if quantum theory were complete, it would imply spooky action at a distance. He and his colleagues proposed that either quantum mechanics was incomplete, or it violated locality and realism in a way that seemed unacceptable. Their hope was that hidden variables, unknown factors, existed beneath quantum mechanics, preserving a classical, local, and realistic world, but hidden from direct measurement. Decades later, in 1964, physicist John Bell formulated what became a decisive test. Bell's theorem showed that if local realism is true, then certain statistical inequalities, now called Bell inequalities, must always be satisfied in experiments involving entangled particles. Quantum mechanics, on the other hand, predicts violations of these inequalities under specific conditions. Thus, experiments could decide between the two worldviews, local realism versus quantum entanglement. In the decades that followed, a series of increasingly sophisticated experiments tested Bell's inequalities, culminating in the so-called loophole-free tests in the 2010 S. The results were astonishing, but consistent. Quantum entanglement does violate Bell's inequalities. The predictions of quantum mechanics are correct, and no local hidden variable theory can explain the observed correlations. Nature behaves in ways that classical intuition cannot accommodate. Either influences travel faster than light, or objects do not possess definite properties until they are measured, or both. The local realism paradox is not a theoretical musing anymore. It is an experimental fact. Faced with this reality, we are forced to reconsider what we mean by locality and realism. If locality is violated, it suggests that entangled particles influence each other instantaneously, regardless of distance. Measuring the state of one particle instantly affects the state of the other, even if they are separated by light years. However, this influence cannot be used to send information faster than light, preserving the overall framework of relativity, but at the cost of a deeply non-local underlying reality. In this view, space-time is not the ultimate stage of events. It is merely the visible surface of a deeper interconnected fabric where distance and separation lose their meaning. If realism is violated instead, then objects do not have definite properties until they are measured. A particle's position, spin, or polarization is not a hidden certainty waiting to be revealed. It is an undefined possibility that crystallizes into a reality only upon observation. The world is not composed of things, but of potentialities. Reality is fundamentally indeterminate until interaction or observation brings it into being. This interpretation, unsettling as it may be, aligns closely with the Copenhagen interpretation of quantum mechanics. There is, of course, a third possibility, that both locality and realism must be abandoned. Some interpretations of quantum mechanics, like relational quantum mechanics or cubism, quantum Bayesianism, suggest that quantum properties are not absolute but relative to the observer. Reality is not a single objective structure, but a patchwork of perspectives, each observer weaving their own version of the universe through their interactions. In such a picture, reality is not a static landscape waiting to be surveyed. It is a dynamic, evolving interplay of observations and measurements. The philosophical implications of the local realism paradox are staggering. If locality fails, the universe is deeply interconnected in ways that transcend space and time. If realism fails, reality itself is not a given but a process, a becoming rather than a being. Either way, the classical world we experience is not the ultimate reality but an emergent approximation, a smooth illusion rising from the churning quantum foam underneath. These ideas have not remained confined to philosophical musings. They have practical consequences too. Quantum technologies like quantum cryptography and quantum teleportation exploit the non-local correlations of entanglement. Quantum computing harnesses the probabilistic superpositions of non-realistic quantum states. Our ability to manipulate and utilize quantum weirdness depends precisely on the very features that violate local realism. In a deep irony, we are building technologies rooted in the recognition that the universe is far stranger than classical physics ever imagined. And yet, despite these advances, no consensus exists about how to interpret the local realism paradox. Some physicists lean toward accepting non-locality while clinging to realism. Others embrace non-realism while defending locality. A few seek hidden variable theories that might salvage both principles, though such theories must be deeply non-local, like Bohmian mechanics, which posits a guiding wave that connects particles across space instantaneously. There are even those who suggest that our very concepts of space, time, and causality may need revision. In the emerging fields of quantum gravity and string theory, space-time itself may not be fundamental but emergent, arising from more primitive quantum processes. If space and time are not fundamental, then non-locality may not be a violation of structure, but a glimpse into a deeper layer of reality, where distance and separation are meaningless constructs of a coarser-grained description. The local realism paradox thus stands as one of the greatest invitations and challenges to human thought. It tells us that beneath the solid, predictable world of our senses lies a domain where connection defies distance, where existence defies definition, where reality defies our expectations. It reminds us that our theories are not just tools for prediction, but mirrors held up to nature, mirrors that sometimes show us not our own reflections, but a stranger and more wondrous face than we ever imagined. As we continue to probe the quantum world, we may find new ways to refine our understanding, new theories that better capture the paradoxical dance of locality, realism, and quantum entanglement. Or we may come to accept that the ultimate nature of reality is beyond the reach of classical thought, that to see clearly, we must first let go of the assumptions that have guided us for centuries. Either way, the local realism paradox ensures that the quest for understanding remains alive, vibrant, and humbling. For in the shimmering mystery of the quantum world, we catch glimpses not just of particles and fields, but of the profound strangeness at the heart of existence itself. Center of the universe paradox. When we look up at the night sky, we are tempted to imagine the universe as a great sphere stretching outward in all directions, with Earth perhaps near the middle or somewhere identifiable in its vast expanse. Our human instincts long for a center, a point from which everything radiates, a cosmic heart around which the stars and galaxies are arranged. But as we peer deeper into the structure of the cosmos, guided by the revelations of modern astronomy and cosmology, we encounter a strange and humbling truth. The universe is expanding, yet it has no center. Every point moves away from every other point, not because everything is rushing outward from a central location, but because space itself is stretching. This unsettling realization gives rise to the center of the universe paradox, a profound puzzle that challenges our intuition and forces us to reimagine what it means for something to grow without growing from a particular place. The story begins with Edwin Hubble's discovery in the 1920s that galaxies are moving away from us and that their recession speed is proportional to their distance. This relationship, now known as Hubble's law, suggested that the universe itself was expanding. But this expansion is not like an explosion from a single point into surrounding emptiness. Instead, the fabric of space itself stretches uniformly, carrying galaxies along with it like raisins embedded in a rising loaf of bread. In this analogy, no raisin is privileged. No spot in the dough marks a special location. Every raisin sees the others moving away, and every point within the dough experiences expansion in the same way. This leads to a staggering conclusion. There is no center to the universe, no privileged point from which the expansion began. The Big Bang, the moment when the universe as we know it began, did not occur at a specific location in space. It happened everywhere simultaneously. Every point in the universe was once compressed into an unimaginably hot, dense state, and the subsequent expansion is not the movement of matter through space, but the expansion of space itself. The center of the universe paradox challenges our everyday notions of motion, origin, and structure. In the world we are used to, explosions have centers, expanding ripples have epicenters. Movement implies a point of departure. But in the cosmos, expansion is not away from a center, it is intrinsic to space. There is no external vantage point from which we could look down upon the universe and see it expanding outward from a single point. From every location, the view is the same. Galaxies receding, space stretching, distances increasing. The universe has no edge, no boundary, and no center. It is a dynamic fabric, growing uniformly in all directions. This is not just a philosophical abstraction. It is built into the very equations of general relativity, the theory that governs the behavior of space-time. Einstein's equations describe a universe that can expand or contract, curve or warp, but do so without requiring a special point of origin within space. In cosmology, this leads to the concept of a homogeneous and isotropic universe, one that looks the same in every direction, isotropic, and at every location, homogeneous, when viewed on sufficiently large scales. Small structures like stars, galaxies, and clusters create local irregularities, but the universe as a whole exhibits a remarkable large-scale uniformity. The center of the universe paradox also has implications for how we think about the Big Bang itself. When we speak of the Big Bang, it is tempting to imagine it as an explosion in space. But it was not an explosion into space. It was an explosion of space. Space and time themselves were created in that primordial moment. Asking where the Big Bang happened is like asking where the surface of a balloon exists as it is inflated. The surface is everywhere, and the expansion happens across the whole surface simultaneously. Similarly, the Big Bang occurred everywhere in the early universe at once. Another way to picture it is to imagine an infinite sheet of rubber being stretched evenly. Every point on the rubber moves away from every other point, but there is no single center of stretching. The sheet expands uniformly, and the stretching is a property of the rubber itself. In the case of the universe, The rubber is space-time, and the galaxies are not flying through it as bullets through air, but are being carried apart by the expansion of the space between them. Yet, despite these elegant models and analogies, the idea that there is no center remains deeply counterintuitive. Our minds crave reference points. We want to draw a map, to put a marker down and say, "Here it all began." But the universe denies us that comfort. Its expansion is not from somewhere, it is expansion of the very fabric of existence. Even if we imagine traveling at unimaginable speeds, we would find no special place, no cosmic hub, no central beacon from which the universe unfolded. This paradox also extends to the idea of the observable universe. From Earth, we can only see a finite region of the cosmos, the sphere of space from which light has had time to reach us since the Big Bang, about 13.8 billion years ago. This observable universe does have a center, us, because we define it relative to our location. But this is not a center of the universe itself, it is merely the center of our particular view. Every observer, on every planet around every star, would see themselves at the center of their own observable universe. In this sense, the universe appears centered wherever you happen to stand. But the true, underlying cosmos has no center at all. Some might ask whether the expansion implies that the universe is infinite. The answer is subtle. The observable universe is finite, bounded by the distance that light has traveled since the beginning. But the entire universe could be infinite. It may have no edge, no boundary, extending endlessly in all directions. In an infinite universe, the paradox becomes even sharper. An infinite cosmos expanding uniformly, with no edges and no center. A boundless sea of space, unfurling forever into itself. The center of the universe paradox thus invites a profound shift in perspective. It asks us to let go of the idea of privileged places, of fixed points, of central origins. It reveals a universe without a favored viewpoint, a cosmos where the laws of physics hold equally everywhere, and where expansion is not a journey from here to there, but an unfolding of space itself. It humbles us, reminding us that our instincts, honed for life on a tiny planet in a small corner of one galaxy, are poorly equipped for grasping the true nature of the cosmos. The paradox is not a flaw or a failing of our models. It is a feature of the universe itself, a testament to the strangeness and grandeur of the reality we inhabit. It shows us that the cosmos is not a simple arena for objects to move within, but a dynamic, evolving entity, a fabric that stretches, curves, and expands without need for a center. It invites us to embrace a new kind of thinking, one that accepts that in the grandest scales of existence, our longing for a center must yield to a deeper, more expansive vision. And perhaps, in that letting go, we glimpse something even more beautiful than a center, a universe where every point is equally part of the whole, where no place is privileged, where existence itself is the center, everywhere and nowhere, all at once. Dark matter-free galaxies paradox. For decades, dark matter has been one of the most essential and enduring components of modern cosmology. Invisible yet influential, dark matter is believed to make up about 85% of the total matter in the universe. Though it does not emit, absorb, or reflect light, its gravitational pull is necessary to explain why galaxies rotate as they do, why clusters of galaxies stay bound together, and how cosmic structures formed in the early universe. Without dark matter, our best models predict that galaxies should tear themselves apart, unable to hold their spinning stars together. Dark matter is the unseen scaffold upon which the visible universe is built, or so we have believed. But in recent years, astronomers have discovered a small number of galaxies that appear to have little or no dark matter at all. This puzzling revelation is known as the dark matter-free galaxies paradox, and it challenges the very foundations of the cosmic picture we have painstakingly constructed. The paradox first burst into prominence with the discovery of galaxy NGC 1052 DF2, a diffuse, faint galaxy located about 65 million light-years from Earth. When scientists measured the motion of star clusters within DF2, they found that the stars moved much more slowly than expected. If dark matter were present in normal quantities, it would create a deep gravitational well, causing stars and clusters to orbit rapidly. Instead, the observed motions indicated that the visible matter, the stars themselves, accounted for nearly all of the galaxy's mass. Essentially, DF2 appeared to have no significant dark matter component. Shortly afterward, another galaxy, NGC 1052 DF4, exhibited similar properties, reinforcing the idea that dark matter-free galaxies might not be unique anomalies. This finding was deeply surprising because the standard model of cosmology, lambda-cold dark matter, predicts that dark matter is an essential ingredient in galaxy formation. Galaxies form when clouds of gas collapse inside massive dark matter halos. The gravitational pull of the dark matter gathers the gas, compresses it, and allows stars to form. Without a surrounding dark matter halo, gas clouds would dissipate before enough material could collect to ignite the birth of a galaxy. How, then, could DF2 and DF4 exist? How could they form, survive, and maintain coherence without the gravitational glue of dark matter? Several possible explanations have been proposed, each fascinating and each fraught with further questions. One idea is that these galaxies were formed under special circumstances. Perhaps they are tidal dwarf galaxies, created not through the traditional collapse of dark matter halos, but through the gravitational interactions of larger galaxies. When two galaxies collide or pass near each other, tidal forces can rip out streams of gas and stars, which then coalesce into new, smaller galaxies. Because the ejected material comes primarily from the visible matter of the original galaxies, tidal dwarfs might contain little or no dark matter. If DF2 and DF4 are tidal dwarfs, their lack of dark matter would make sense. However, even this explanation is not without difficulties. Tidal dwarfs typically have chaotic, irregular structures and relatively short lifespans. Yet DF2 and DF4 appear stable and coherent, much like conventional dwarf galaxies. Moreover, their environment does not obviously show the debris fields and tidal structures one would expect from recent galactic collisions. Thus, while the tidal dwarf hypothesis remains possible, it does not fully resolve the paradox. Another proposal is that the measurements of mass and motion in these galaxies are flawed or incomplete. Estimating the mass of distant, faint galaxies is notoriously difficult. Small errors in distance measurements, assumptions about the distribution of stars, or the interpretation of velocity data could significantly skew the results. If DF2 and DF4 are farther away than initially thought, for example, they might be larger and more massive than calculated, hiding a normal amount of dark matter within them. Or if we have misjudged the motions of their star clusters, we might be missing hidden gravitational influences. Subsequent studies have refined distance estimates, but the question remains open. Are these galaxies truly dark matter deficient, or are we simply misreading the data? Alternatively, the paradox could hint at something even more profound, that our understanding of gravity itself might be incomplete. If galaxies like DF2 and DF4 can exist without dark matter, perhaps the laws of motion and gravity on cosmic scales differ from those we observe locally. Modified gravity theories, like modified Newtonian dynamics, MON, have long been proposed as alternatives to dark matter. In MOND, the strength of gravity changes at very low accelerations, naturally producing the flat rotation curves observed in galaxies without requiring unseen mass. If MOND, or a similar theory, is correct, then the apparent absence of dark matter in certain galaxies could be a natural consequence of how gravity behaves differently under certain conditions. Yet this explanation raises its own set of challenges. If modified gravity were the correct description of the universe, we would expect it to apply universally, not selectively. Why would some galaxies follow the standard dark matter-dominated pattern, while others appear to lack dark matter altogether? A complete theory must explain not just isolated cases, but the full diversity of cosmic structures we observe. Another speculative possibility is that dark matter itself is more complex than we imagine. Perhaps dark matter can clump, move, or interact in ways that occasionally leave pockets of the universe without significant dark matter presence. Maybe there are processes by which dark matter halos can be stripped away or dispersed, leaving behind galaxies composed almost entirely of baryonic matter, ordinary atoms, and particles. If so, these dark matter-free galaxies could serve as rare but crucial laboratories for understanding the true nature of dark matter. The dark matter-free galaxies paradox thus sits at the crossroads of many of the deepest questions in cosmology. It forces us to confront the limits of our measurements, the assumptions baked into our models, and the very structure of the universe itself. It highlights how even a few anomalies, just a handful of strange galaxies, can shake the foundations of a theory that otherwise explains so much. Science often advances not through the confirmation of existing ideas, but through the patient, sometimes painful exploration of contradictions. The missing dark matter in these galaxies may turn out to be a mistake, an illusion created by distance or data, but it may also be a crack in the edifice of current cosmology, an invitation to build a deeper and more complete understanding of the universe. As astronomers continue to hunt for more dark matter-deficient galaxies, and as instruments become more precise, we may soon have clearer answers. Are DF2 and DF4 unique accidents, or are they the tip of a hidden cosmic iceberg? Are we seeing the birth of a new class of galaxies, or glimpsing flaws in the way we measure and interpret the distant universe? Whatever the answer, the search itself enriches our journey toward the truth. The dark matter-free galaxies paradox reminds us that the universe is under no obligation to conform to our expectations. It is a dynamic, evolving reality, full of surprises and mysteries that challenge our intellect and our imagination. And perhaps, hidden in the faint light of these strange galaxies, we will find not only the solution to a paradox, but a new key to the deeper architecture of the cosmos itself. Red-hot Jupiter's paradox. When astronomers first began discovering planets orbiting stars beyond our sun, they expected to find worlds like those in our own solar system. It seemed logical to assume that small, rocky planets would orbit close to their stars, while giant gaseous planets would stay farther out, where temperatures were cool enough for gas and ice to coalesce. After all, that is the arrangement we see here. Mercury, Venus, Earth, and Mars circle the Sun in tight, warm orbits, while Jupiter, Saturn, Uranus, and Neptune reside in the frigid outer reaches. But the first discoveries shattered that comfortable expectation. Instead of cold, distant giants, astronomers found enormous planets, many larger than Jupiter, orbiting scorchingly close to their stars, sometimes completing an orbit in mere days. These strange worlds, dubbed hot Jupiters, presented a profound puzzle now known as the red-hot Jupiter's paradox, forcing us to rethink everything we thought we knew about how planets form and evolve. Hot Jupiters defy the traditional model of planetary system formation known as the nebular hypothesis. According to this model, planets form from a disk of gas and dust surrounding a young star. Close to the star, the disk is hot, and only metals and silicates can condense into solid grains, leading to the formation of small rocky planets. Farther out, beyond the so-called frost line, temperatures are low enough for volatile compounds like water, methane, and ammonia to freeze into ices, providing the raw material for large cores that can then accumulate thick atmospheres of hydrogen and helium, creating gas giants. In this framework, giant planets should form only beyond the frost line, where ices are abundant and growth is rapid. Yet hot Jupiters orbit at distances much closer than Mercury's distance from the Sun. They are exposed to intense stellar radiation, with temperatures on their cloud tops soaring to over 1,000 degrees Celsius. The conditions where they now reside are utterly hostile to the process of gas giant formation. The materials needed to build such planets simply could not exist in significant quantities so close to a star. How then did these massive planets come to orbit in such inhospitable locations? One leading explanation is planetary migration. In this scenario, hot Jupiters formed far from their stars, beyond the frost line where conditions were right for gas giant formation. Afterward, they somehow migrated inward, traveling across vast distances to settle into tight, sizzling orbits. Several mechanisms have been proposed to account for this migration. One possibility is that interactions between the young planet and the surrounding protoplanetary disk caused it to spiral inward. As a massive planet orbits within a disk of gas, gravitational interactions can create waves or wakes in the disk. These waves exert torques on the planet, causing it to lose angular momentum and move closer to the star. This process, known as disk-driven migration, can be rapid, potentially moving a giant planet from beyond the frost line to a close orbit within just a few million years. Another migration mechanism involves gravitational interactions between planets. In a crowded planetary system, giant planets can scatter off one another through close encounters, changing their orbits dramatically. One planet might be flung outward, while another plunges inward, settling into a tight orbit after its trajectory is altered. In some cases, interactions with a distant stellar companion or other perturbing body could cause a planet's orbit to become highly elliptical, bringing it dangerously close to the star at its nearest point. Tidal forces would then circularize the orbit over time, leaving the planet in a close, nearly circular orbit, basking in its star's intense heat. Yet both migration scenarios raise further questions. If giant planets commonly migrate inward, why did Jupiter, Saturn, and the other gas giants in our own solar system remain in the outer regions? Did they avoid migration by chance, or were conditions in our solar nebula somehow different? Moreover, if migration is so efficient, why do we still find systems with multiple, well-ordered planets on wide, stable orbits? The existence of hot Jupiters suggests that violent migrations are possible, even common, but the diversity of planetary systems we observe hints that migration is not inevitable. There must be additional factors, timing, mass, disk properties, that determine whether a gas giant migrates or remains anchored in the cold. Another layer of the red-hot Jupiter's paradox concerns the survival of the migrating giants. As a planet spirals inward, it must pass through regions of the disk where conditions are highly turbulent. Why do some planets survive this perilous journey intact, while others are presumably engulfed or destroyed? In theory, if migration proceeds unchecked, many planets should plunge directly into their stars. The fact that we observe a large number of hot Jupiters suggests that something halts their inward drift, parking them in stable, close-in orbits. Theories propose that magnetic fields, stellar winds, or inner cavities in the protoplanetary disk could act as barriers, stopping the migration before it is too late. Yet the precise balance of forces remains an open question, still being explored through simulations and observations. Interestingly, hot Jupiters seem to have peculiar effects on their host stars and on any neighboring planets. Many stars with hot Jupiters show signs of enhanced activity, stronger magnetic fields, faster rotation, possibly stirred by the gravitational tug of their massive companions. Furthermore, systems with hot Jupiters often lack other nearby planets, suggesting that the inward migration of a gas giant may disrupt or even destroy inner rocky worlds. In this view, the presence of a hot Jupiter could spell doom for any emerging terrestrial planets, sweeping the inner system clean and leaving only the giant survivor in a close, solitary orbit. Thus, the red-hot Jupiter's paradox not only challenges our understanding of how planets form, but also how planetary systems evolve and what conditions are necessary for life. If hot Jupiters are common, and if their migration often sterilizes planetary systems, then the serene, life-friendly arrangement of our solar system may be more unusual than we once thought. Perhaps the rarity of Earth-like worlds is not due only to the difficulty of forming rocky planets, but also to the violent dynamics that can unfold in young systems, where giant worlds can rampage inward and reshape the fates of smaller worlds. In recent years, the discovery of warm Jupiters, gas giants at intermediate distances, and even ultra-hot Jupiters with temperatures exceeding 2,000 degrees Celsius has enriched the mystery. Some hot Jupiters are tidally locked, presenting the same face to their star at all times, creating hellish environments of permanent day and night. Others show puzzling atmospheric phenomena, such as superheated stratospheres, strange chemical compositions, and winds roaring at thousands of kilometers per hour. These exotic conditions offer new laboratories for studying atmospheric physics under extreme conditions, but they also emphasize how alien these worlds truly are compared to anything in our solar system. Ultimately, the red-hot Jupiter's paradox reminds us that the universe often defies our expectations. Nature is not obligated to mirror the familiar patterns we observe close to home. Instead, it reveals a richness and diversity of planetary systems far beyond what we once imagined. Hot Jupiters stand as monuments to the creative and sometimes violent forces that shape worlds, testifying to the dynamism and unpredictability of the cosmos. As astronomers continue to survey the skies with missions like TESS, CHEOPS, and the James Webb Space Telescope, they are uncovering ever more worlds, some hot, some cold, some lonely, some part of intricate systems. Each new discovery adds a piece to the puzzle, helping to unravel the histories written into the orbits of distant planets. In doing so, we not only seek to understand the fate of hot Jupiters, but also to glimpse the broader story of how planetary systems are born, evolve, and sometimes, against all odds, provide havens for life. Gamma-ray burst paradox. Across the silent, black tapestry of the universe, there occur moments of unimaginable violence. In the aftermath of a dying star's collapse or the merger of two neutron stars, titanic explosions erupt, sending out colossal bursts of gamma rays, the most energetic form of light. These events, known as gamma-ray bursts, are among the most luminous phenomena in the cosmos, outshining entire galaxies for a few fleeting moments. Their energies are so intense that, if a GRB were to occur within a few thousand light-years of Earth and aim directly at us, it could strip away our atmosphere and extinguish life. Yet beyond their terrifying power and their mystery-shrouded origins, gamma-ray bursts have presented physicists with a subtle but profound puzzle: the gamma-ray burst paradox. Observations suggest that photons within these bursts, traveling vast cosmic distances, sometimes arrive at Earth having changed direction slightly, something that defies classical expectations of how light should move through the emptiness of space. At first glance, the behavior of light seems simple. Photons, particles of light, should travel in straight lines through the vacuum of space, unless acted upon by gravity or material objects. The universe, vast and mostly empty, provides little to interfere with their journey. In Einstein's relativity, the path of a photon is determined by the curvature of space-time and, absent any intervening matter or strong gravitational fields, light should move along a straight trajectory without deviation. Yet when scientists studied gamma-ray bursts in fine detail, they noticed something odd. The directions of incoming photons, particularly the highest energy ones, sometimes appeared subtly misaligned with the expected path. These tiny shifts could not be explained by gravitational lensing, interstellar dust, or instrumental error alone. Instead, they hinted that something unexpected might be happening to photons as they crossed the vastness between stars and galaxies. One possible explanation touches on the fabric of space-time itself. In the standard model of physics, the vacuum is not truly empty. It seethes with quantum fluctuations, virtual particles popping into and out of existence at unimaginably small scales. Some speculative theories of quantum gravity suggest that on the Planck scale, about 10 to the power of 35 meters, The smoothness of spacetime breaks down into a foamy, turbulent structure. If this spacetime foam exists, then photons traveling over cosmological distances might interact with it in subtle ways, altering their paths very slightly. Over billions of light years, even the tiniest deviations could accumulate, producing measurable angular shifts in the arrival direction of gamma-ray photons. This idea leads to a deeply unsettling conclusion, that space itself might not be a featureless stage, but a jittery dynamic medium, distorting the paths of particles in ways we can only begin to detect. The paradox, then, is not merely about unexpected photon behavior, but about the nature of reality itself. Light, the most basic messenger across the cosmos, might carry with it the fingerprint of the universe's hidden quantum structure. Another possibility is that gamma-ray bursts themselves, being extreme events involving intense magnetic fields, relativistic jets, and high-energy particles, might somehow imprint complex structures into the outgoing radiation. Perhaps photons are not emitted in perfect synchrony or straight lines, but are scattered, twisted, or refracted within the turbulent environment close to the source. If the jets of matter ejected by a GRB wobble or precess as they shoot into space, the light emitted could be slightly redirected. However, such models must match the detailed timing and angular data we observe, and it remains challenging to fully account for the observed anomalies purely through source-side effects. The gamma-ray burst paradox also invites questions about the limits of fundamental principles like Lorentz invariance, the idea that the laws of physics are the same for all observers, regardless of their relative motion. Some versions of quantum gravity predict tiny violations of Lorentz invariance at extremely high energies, leading to slight energy-dependent shifts in the speed or path of photons. If high-energy photons from GRBs arrive slightly earlier, later, or from different directions than lower-energy ones, it could be a hint that Lorentz symmetry is only an approximation, breaking down at the deepest levels of reality. Detecting such violations would revolutionize physics, pointing toward a unified theory that blends quantum mechanics and general relativity. Adding to the complexity is the sheer variety of gamma-ray bursts themselves. Some last mere milliseconds, others stretch for minutes or longer. Some originate from the deaths of massive stars collapsing into black holes, others from the violent mergers of neutron stars. Each GRB has its own unique energy profile, spectral signature, and afterglow. Yet, across these differences, the paradoxical shifts in photon directions seem to persist, suggesting that whatever mechanism underlies them is not an artifact of a specific type of burst, but something universal, woven into the very propagation of light through space. Observationally, studying gamma-ray bursts presents immense challenges. They are unpredictable, fleeting, and often occur billions of light years away. Capturing them requires a coordinated ballet of satellites, ground-based telescopes, and rapid response systems capable of swinging into action the instant a burst is detected. Instruments like NASA's Fermi Gamma-Ray Space Telescope and the Swift Observatory have provided invaluable data, but they also highlight the tantalizing limits of current technology. Future missions with higher sensitivity and greater angular resolution may finally resolve whether the photon shifts are intrinsic to the bursts or arise during their journey through space. The gamma-ray burst paradox serves as a cosmic reminder that even the most energetic explosions in the universe can carry whispers of subtle mysteries. It suggests that the vacuum of space may not be inert, that spacetime itself may ripple and twist at microscopic scales, and that the photons we so casually detect are not merely travelers but storytellers, bearing hidden tales of the universe's most intimate secrets. In the broader picture, this paradox connects to many of the grandest questions in physics. If spacetime is foamy, how does that affect causality, the structure of black holes, or the birth of the cosmos itself? If Lorentz invariance fails at high energies, What new symmetries or laws replace it? If photons can subtly shift paths without visible cause, what other cosmic messengers, gravitational waves, neutrinos, dark matter particles, might also reveal new facets of reality and their trajectories? Thus, the gamma-ray burst paradox is not an isolated puzzle, but a gateway. It links the violence of dying stars to the gentle, persistent quest to understand the universe's deepest workings. It shows that, even amid chaos and cataclysm, nature's most subtle clues are hidden, tiny deflections in light, nearly imperceptible shifts in direction that can hint at revolutions in understanding. As we refine our instruments and extend our gaze deeper into the cosmic night, we move closer to resolving this paradox. Perhaps future gamma-ray observatories, operating at even higher energies and finer resolutions, will catch the fingerprints of space-time foam. Perhaps novel analyses will reveal systematic patterns in the data, pointing to new physics just beyond our current grasp. Or perhaps we will find that our assumptions about light, about space, about time itself, must be rewritten once again. Whatever the outcome, the gamma-ray burst paradox reminds us of the wonder that still lies hidden in the universe's oldest light. It teaches us that even in the brightest flashes, it is the subtlest shadows that reveal the deepest truths, and that in the endless night between stars, the cosmos still holds secrets waiting to be unveiled. Gravity and space-time paradox. Albert Einstein's theory of general relativity is one of the most beautiful achievements in the history of science. With a few simple yet profound equations, Einstein reimagined gravity not as a force between masses, but as the bending and warping of space-time itself. Massive objects like stars and planets curve the fabric of space-time around them, and other objects move along those curves, tracing the paths we observe as gravitational motion. From the orbits of planets to the bending of starlight to the expansion of the universe, general relativity has passed every observational test thrown at it. It is a towering intellectual triumph, majestic in its simplicity and stunning in its accuracy. And yet, despite its success, Einstein's model of gravity carries within it a fatal flaw, one that becomes glaring when we peer into the very small and the very extreme. When confronted with the strange, jittery world of quantum mechanics, general relativity begins to crack. This profound tension is known as the gravity and space-time paradox, and it sits at the heart of modern physics, unresolved and unsettling. At ordinary scales, the clash between general relativity and quantum mechanics remains hidden. We can calculate planetary orbits, engineer GPS satellites, and predict gravitational waves without worrying about quantum effects. Similarly, the probabilistic world of electrons, photons, and atomic nuclei operates safely at the microscopic level, where gravity's influence is negligible. Each theory reigns supreme in its own domain. But nature is not neatly divided into macroscopic and microscopic kingdoms. There are places, black holes, the Big Bang, the interiors of neutron stars, where the forces of gravity and quantum mechanics must collide. And when they do, our theories crumble into contradiction. The heart of the paradox lies in the nature of space-time itself. In Einstein's theory, space-time is smooth and continuous, like a fabric stretched across the cosmos. It bends under mass and energy, guiding the motion of objects. In quantum mechanics, however, the universe is not smooth but grainy, fluctuating wildly at the smallest scales. According to the Heisenberg uncertainty principle, there is always an inherent jitter, a randomness to the properties of particles and fields. If we apply this principle to space-time, it suggests that at incredibly tiny scales, around the Planck length of 10^35 10 to the power of 35, 10 to 35 meters, space-time should not be smooth, but should fluctuate violently, creating a seething foam of temporary black holes, wormholes, and bursts of energy. This quantum foam completely contradicts the smooth geometry required by general relativity. In Einstein's equations, the curvature of space-time depends smoothly on the distribution of mass and energy. But if space-time itself becomes a chaotic quantum froth at small scales, then the very foundation of the equations breaks down. The concept of a well-defined point in space-time loses meaning. Without smoothness, the classical idea of a gravitational field becomes impossible. Thus, when pushed to the extremes of smallness and high energy, the two pillars of modern physics, relativity and quantum mechanics, collapse into mutual incompatibility. The most glaring manifestation of this paradox occurs at the singularities predicted by general relativity. At the heart of a black hole, or at the moment of the Big Bang, the equations of relativity predict infinite curvature of spacetime, infinite density, infinite gravity, infinite temperature. But infinities are the warning sirens of physics, signaling that a theory has reached the limits of its applicability. Quantum mechanics, with its insistence on uncertainty and finite scales, cannot accommodate true singularities. Something must replace them, a new description of space-time and gravity that is both smooth enough for relativity and jittery enough for quantum uncertainty. Yet, despite decades of effort, no complete theory of quantum gravity has been found. Several approaches have been proposed, each fascinating in its own right. String theory suggests that the fundamental building blocks of nature are not point particles, but tiny vibrating strings, whose different modes of vibration correspond to different particles. In this framework, gravity emerges naturally, and spacetime's geometry becomes an emergent, flexible feature, rather than a rigid backdrop. String theory also implies that spacetime may have more dimensions than the familiar 3 of space and 1 of time, dimensions that are curled up so tightly that we do not perceive them. Another candidate is loop quantum gravity, which takes a different route, attempting to directly quantize spacetime itself. In this view, space is composed of discrete chunks, woven together into a network of finite loops. Geometry becomes a kind of quantum fluid, granular at the smallest scales, but appearing smooth at larger ones. Loop quantum gravity seeks to preserve the successes of general relativity while resolving the singularities that plague it. Yet neither string theory nor loop quantum gravity has produced definitive experimental evidence. Both remain mathematically rich but empirically elusive, and so the gravity and space-time paradox remains, a deep, unsettling gap at the core of our understanding of reality. We know that both quantum mechanics and general relativity work incredibly well in their respective domains. We know they must somehow be reconciled. But the path to that reconciliation remains hidden, tantalizing, and frustrating. This paradox also reverberates through our understanding of black holes. According to classical relativity, information falling into a black hole is lost forever once it crosses the event horizon. But quantum mechanics insists that information can never be truly destroyed. This conflict leads to the famous black hole information paradox, a specific battleground where the broader gravity and space-time paradox plays out in dramatic terms. Resolving the fate of information in black holes may be a key to unlocking the deeper structure of quantum gravity itself. Cosmology, too, is touched by the paradox. The earliest moments of the universe immediately following the Big Bang must have involved densities and energies so extreme that quantum gravitational effects were dominant. Without a theory that unites quantum mechanics and gravity, we cannot fully understand the true beginning of the universe. Inflation, cosmic microwave background fluctuations, the seeds of galaxy formation, all are tied in ways we do not yet fully grasp to the missing quantum theory of spacetime. Thus, the gravity and spacetime paradox is not an abstract problem confined to blackboards and ivory towers. It is a living frontier, a doorway to a deeper understanding of the cosmos. It reminds us that our current theories, for all their power and elegance, are provisional. They are maps, not the territory. The true nature of space-time, gravity, and quantum reality lies just beyond the horizon of our knowledge, waiting to be discovered. As we build more powerful particle colliders, launch more sensitive gravitational wave detectors, and develop new mathematical frameworks, we may inch closer to that discovery. Perhaps clues lie hidden in the subtle distortions of space-time recorded by LIGO and Virgo, or in the afterglows of black hole mergers, or in the intricate patterns of cosmic background radiation, or perhaps they wait in phenomena we have not yet imagined, whispers from the quantum fabric of the cosmos. The gravity in space-time paradox is a testament to the ongoing adventure of human thought. It tells us that even our greatest triumphs are not the final word, but milestones on a longer journey. It invites humility, awe, and wonder. For beyond the smooth curves of Einstein's spacetime and the jittering uncertainties of quantum fields, the universe hides a deeper truth, a truth that, one day, we may finally come to understand. Cosmic microwave background and isotropy paradox. When we gaze into the depths of space with radio telescopes tuned to the faintest signals, we detect a ghostly afterglow, the cosmic microwave background, or CMB. This ancient radiation is the oldest light in the universe, a remnant from a time about 380,000 years after the Big Bang, when the universe cooled enough for atoms to form and light to travel freely through space. The CMB offers a snapshot of the infant cosmos, a portrait of the universe as it was in its earliest accessible moments. But as scientists mapped this primordial light with increasing precision, they stumbled upon a profound and puzzling feature. The CMB is astonishingly uniform in every direction we look. No matter where we point our instruments, the temperature of the background radiation is almost exactly the same, varying only by 1 part in 100. 0. This smoothness gives rise to the cosmic microwave background and isotropy paradox, a mystery that challenges our understanding of how the universe evolved and why it appears so uniform without requiring a central point of expansion. At first glance, the uniformity of the CMB might seem like a natural result of a Big Bang that occurred simultaneously everywhere, but on closer inspection, it presents a deep conundrum. According to the standard Big Bang model, regions of space separated by large distances should not have been able to influence each other in the early universe. The speed of light sets a cosmic speed limit, and in the brief time since the universe's beginning, distant parts of the cosmos should not have had enough time to exchange information, energy, or heat. This means that there is no reason why one patch of the CMB sky should have exactly the same temperature as a patch billions of light years away in the opposite direction. And yet, they do. This paradox is often framed through the concept of causally disconnected regions. Imagine the early universe as a patchwork of zones, each expanding and cooling independently. Without communication between these zones, we would expect to see significant temperature differences across the sky, some regions hotter, some cooler, reflecting the random conditions present in each isolated zone. Instead, we observe an extraordinary isotropy. The universe looks almost exactly the same in every direction, suggesting a level of coordination that should be impossible under the basic rules of the early cosmic expansion. The isotropy of the CMB also feeds into the larger center of the universe paradox. In a universe with a true center, one might expect to see a gradient in the CMB. The radiation would appear hotter in one direction, cooler in another, depending on our position relative to the center. But no such gradient exists. Observers anywhere in the universe would see the CMB as remarkably uniform, suggesting that the universe has no center at all, or that the expansion of the universe happened everywhere at once, in a way that preserves isotropy on the largest scales. To resolve these puzzles, cosmologists introduced the theory of cosmic inflation in the early 1980s. Inflation posits that a tiny fraction of a second after the Big Bang, the universe underwent a brief but stupendously rapid expansion, stretching spacetime itself by a factor of at least 102,610 to the power of 26. 10 to 26, in an infinitesimal sliver of time. During this inflationary epoch, regions that were once small enough to be in causal contact, able to exchange light and heat, were blown up to cosmic scales. As a result, the uniformity we see today reflects the conditions that prevailed before inflation took place. Inflation smoothed out the wrinkles, stretched the initial fluctuations, and set the stage for the universe's remarkably homogeneous and isotropic appearance. While inflation provides an elegant solution to the isotropy paradox, it raises new questions of its own. What mechanism drove inflation? What caused it to start, and what caused it to end? Why was the universe in such a uniform state even before inflation began? These remain open mysteries, suggesting that while inflation is a powerful idea, it may not be the final word. Moreover, the slight irregularities that do exist in the CMB, the tiny fluctuations of temperature at the level of 1 part in 100,000, carry profound importance. These small ripples are believed to be the seeds from which all cosmic structure grew: galaxies, clusters, and the great cosmic web of matter. Without these tiny deviations from perfect uniformity, the universe would be a featureless, homogeneous fog, devoid of stars, planets, and life. Thus, while the CMB's isotropy is striking, it is the delicate imperfections that ultimately gave rise to everything we see today. The uniformity of the CMB also emphasizes a deep principle in cosmology called the cosmological principle, the assumption that the universe is homogeneous and isotropic on large scales. This principle underpins much of modern cosmology, allowing scientists to model the universe with a handful of parameters. Yet it is ultimately an assumption, one validated by observations like the CMB, but still conceptually profound. It means that there are no special places in the universe, no preferred directions, no cosmic center. Every point is as good as any other. The laws of physics and the structure of the universe are the same everywhere and in all directions. Yet this lack of a center, coupled with the CMB's isotropy, leaves us with a lingering sense of unease. How can the universe have begun without a central point of expansion? How can every observer, no matter where they are, see themselves at the center of the observable universe? The answer lies in the nature of space-time itself. The Big Bang was not an explosion into space, but an expansion of space itself. Every point in the early universe expanded away from every other point, and that expansion continues today. There is no center because the expansion is uniform. It happens everywhere, all at once. In this sense, the universe can be thought of like the surface of a balloon being inflated. As the balloon expands, every point on its surface moves away from every other point. There is no center on the surface itself. The center lies outside the two-dimensional surface in a third spatial dimension we cannot access from the surface alone. Similarly, if our universe is a three-dimensional surface embedded in a higher dimensional reality, the true center might lie beyond our observable 3 dimensions, or there might be no center at all, just an intrinsic expansion of space itself. The cosmic microwave background and isotropy paradox thus invites us into a more radical understanding of the cosmos. It suggests a universe without preferred locations, without central hubs, without edges. It paints a picture of a reality in which every observer, on every planet, in every galaxy, sees the same grand design unfolding around them. It humbles our sense of importance and reminds us that while we occupy a tiny corner of the universe, the laws that govern us are the same laws that govern the whole. As we continue to refine our observations of the CMB with instruments like the Planck satellite and future missions to come, we may find even subtler hints, anomalies, asymmetries, or variations that challenge or deepen our understanding. Perhaps we will uncover evidence for new physics beyond inflation, or hints of structures beyond the observable horizon, or perhaps we will find that the universe's extraordinary isotropy is even more profound and complete than we currently imagine. Either way, the cosmic microwave background and isotropy paradox remains a profound reminder that the universe's greatest mysteries are often hidden not in its wildest extremes, but in its most perfect symmetries. In the quiet uniformity of the oldest light, we hear an ancient whisper, a message from the dawn of time, still rippling through the fabric of existence, inviting us to wonder, to question, and to seek deeper understanding. Dark flow paradox. The universe, on its largest scales, is often described as a vast, expanding ocean of galaxies. Galaxies are not fixed points in space, but are carried outward by the relentless expansion of the cosmos, like corks floating on the surface of an inflating balloon. This expansion, mapped so precisely by Hubble's law, is supposed to be uniform, driven by the smooth fabric of space-time, stretching equally in all directions, while local motions, small gravitational tugs, and chaotic interactions cause nearby galaxies to dance irregularly. The overall flow should be random once we look at scales large enough to average out these local disturbances. Yet in the late 2000s, astronomers detected something deeply puzzling. A large number of galaxy clusters appeared to be moving coherently, flowing together in a particular direction as if drawn by a gravitational force from beyond the visible universe. This discovery, now known as the dark flow paradox, suggests the presence of a deep, unseen structure, or an entirely new feature of cosmology that challenges our most fundamental assumptions about the cosmos. The discovery of dark flow came through the careful observation of the cosmic microwave background, the faint afterglow of the Big Bang that permeates all of space. Specifically, astronomers used the kinematic Sunyaev-Zeldovich effect, a subtle distortion of the CMB caused when photons scatter off hot gas in galaxy clusters. If a cluster is moving relative to the cosmic background, it leaves a small but measurable imprint in the CMB. By analyzing these distortions across hundreds of galaxy clusters, researchers found evidence that many clusters, over regions spanning billions of light-years, were drifting in the same direction at unusually high speeds, up to 1,000 kilometers per second. This coherent motion could not easily be explained by the known distribution of matter within the observable universe. The gravitational influence of nearby superclusters, or the large-scale structure of galaxies, should cause random motions, small eddies and swirls, not a single sweeping flow. The dark flow paradox, then, suggests the possibility of something massive, something far beyond the edge of what we can see, exerting a gravitational pull on these clusters, guiding them along an unseen current toward an unknown destination. One possibility is that our observable universe is only a small part of a much larger multiverse. If regions beyond our cosmic horizon contain massive concentrations of matter, enormous structures, or even other bubble universes, they could tug on the galaxies within our observable sphere, inducing the flow we observe. In this view, dark flow is not just a quirk of local structure, but a whisper from realms we cannot yet perceive, evidence that our universe is embedded in a far grander and more complex cosmic landscape. Alternatively, dark flow might point to previously unrecognized features within our own universe. Perhaps massive structures, vast walls or voids stretching across hundreds of millions of light-years exist just beyond our observational limits. Their gravitational fields could influence the motion of galaxy clusters in our vicinity. However, this would imply that the universe is not as homogeneous as we had assumed on the largest scales, challenging the cosmological principle that underpins much of modern cosmology. Another possibility is that dark flow reflects a breakdown in our understanding of gravity itself. If gravity behaves differently over extreme distances, or if additional forces are at play on cosmological scales, then the observed coherent motion could be a natural outcome. Modified gravity theories like MOND or extensions of general relativity might provide alternative frameworks in which dark flow arises not from unseen mass, but from new laws of physics waiting to be uncovered. Yet, Despite its profound implications, the existence of dark flow remains controversial. Subsequent studies using newer, more precise CMB data have struggled to confirm the original findings. Some researchers argue that the signal detected was a statistical fluke, an artifact of noise and limited data. Others point to methodological uncertainties in measuring the kinematic Sunyaev-Zeldovich effect, which is incredibly subtle and prone to contamination from other sources. As with many discoveries on the cutting edge of science, confirmation or refutation requires time, better instruments, and careful, skeptical analysis. Nevertheless, the dark flow paradox remains a tantalizing possibility. If confirmed, it would force a dramatic revision of our understanding of the universe's structure, origin, and fate. It would suggest that the universe is not only expanding, but that its expansion is being shaped by forces and structures we cannot yet see. It would hint that our cosmic horizon, the limit of the observable universe, is not the true boundary of existence, but merely the edge of our current knowledge. The philosophical implications of dark flow are as profound as the scientific ones. It challenges the comforting notion that we live in a representative patch of the universe, that the cosmos looks the same in all directions and at all distances. It suggests instead that we might occupy a particular place in a much vaster and more varied multiverse, subject to influences from regions forever beyond our reach. It hints that the ultimate structure of reality is larger, stranger, and more interconnected than we have dared to imagine. Moreover, dark flow touches on the deep human desire to know what lies beyond. Throughout history, every horizon we have encountered has proven to be only a temporary limit, one that we eventually cross, understand, and expand. If dark flow is real, it represents a new kind of horizon, not just a boundary of distance, but a boundary of knowledge. It suggests that there are forces shaping our universe from beyond what we can ever observe, forces that whisper of a grander reality we may never fully comprehend. Future missions and observations may help resolve the paradox. More sensitive surveys of the CMB, improved measurements of galaxy cluster motions, and deeper maps of the large-scale structure of the universe could either confirm the existence of dark flow or reveal it as an illusion. Instruments like the upcoming Euclid spacecraft and the Nancy Grace Roman Space Telescope may provide new data that sharpen our view of cosmic motion. Even if dark flow itself proves elusive, the search will undoubtedly enrich our understanding of cosmic dynamics and the true nature of the universe. In the meantime, the dark flow paradox stands as a powerful symbol of the frontier spirit in cosmology. It reminds us that even in an era of precision measurements and sophisticated models, the universe still harbors mysteries vast enough to humble our ambitions. It teaches us that the greatest discoveries often begin not with answers, but with anomalies, those small, stubborn deviations from expectation that whisper of hidden truths. As we continue to explore the cosmos, we are likely to encounter many such paradoxes, each one a doorway to deeper understanding. And perhaps in the dark currents that seem to tug at distant galaxies, we glimpse not only the gravitational pull of unseen masses, but the pull of mystery itself, the eternal invitation to look beyond what is known, to wonder, and to seek. Reality as a quasi-crystal paradox. When we open our eyes to the world around us, reality appears smooth, continuous, and seamless. Space stretches outward in an unbroken canvas, and consciousness flows in an endless, intuitive stream. Everything about our experience suggests continuity. Yet at the bleeding edge of physics, mathematics, and philosophy, a strange and radical idea has begun to emerge, an idea that challenges the very foundation of what we think space, time, and consciousness are made of. According to a new line of thinking, reality may not be smooth at all. It might be discrete, pixelated, built not from seamless fabric but from tiny, indivisible units arranged in intricate patterns. Even stranger, this underlying structure might not be regular like a simple crystal, but organized according to the mathematics of a quasi-crystal, a structure that is ordered but never quite repeating. This is the reality as a quasi-crystal paradox, and it proposes a cosmos so profoundly alien to our everyday intuition that it forces us to question whether we have ever truly understood space, time, or even our own minds. The notion of reality as a quasi-crystal stems from efforts to unify quantum mechanics and general relativity to find a model of reality that works at both the largest and smallest scales. Traditional approaches, like string theory and loop quantum gravity, envision spacetime as either an emergent phenomenon or a network of discrete connections. But quasi-crystal models take this idea further. They propose that at the most fundamental level, reality itself is made up of a static, high-dimensional pattern that projects into the three-dimensional world we experience. In this picture, the universe is not a continuous flow, but a projection of a higher-order, quasi-crystalline structure, much like a hologram projected from a complex interference pattern. A quasi-crystal is a special kind of structure, first discovered in materials science in the 1980s. Unlike ordinary crystals, which have repeating periodic patterns, quasi-crystals exhibit order without repetition. Their arrangements are deterministic, but never quite repeating, creating complex patterns like Penrose tilings that fill space without ever looping back. Quasi-crystals exhibit symmetries, such as five-fold rotational symmetry, that are forbidden in ordinary crystals. They represent a kind of middle ground between perfect order and pure randomness, an intricate dance of patterns that hint at deeper levels of mathematical beauty. When applied to the fabric of reality itself, the quasi-crystal model suggests that space, time, and matter emerge from the projection of a higher dimensional quasi-crystal down into our familiar three-dimensional world. Reality, in this view, is pixelated at the Planck scale, the smallest possible unit of length, about 10 to the power of minus 35 meters. But unlike a simple grid of points, these pixels are arranged according to a quasi-crystalline pattern, weaving an underlying order far richer and more complex than anything we normally imagine. The reality as a quasi-crystal paradox arises when we confront the consequences of such a model. If reality is fundamentally discrete and quasi-crystalline, then our classical notions of continuity, locality, and even causality are illusions, emergent properties that arise from the coarse-grained experience of a deeper, pixelated substrate. The very idea of moving smoothly through space becomes a convenient fiction. In truth, what we perceive as motion may be the sequential activation of quasi-crystal nodes, like the frame-by-frame flicker of an impossibly high-resolution cosmic film. Moreover, this model suggests that consciousness itself might be intimately linked to the structure of the quasi-crystal. Some theorists speculate that the patterns of the quasi-crystal are not merely passive scaffolds, but active participants in the emergence of mind. Consciousness, in this view, could arise from the specific way information flows through the quasi-crystalline network. The brain, rather than generating consciousness in isolation, might instead tap into a deeper informational substrate, a universal mind-like pattern embedded in the geometry of existence itself. Such ideas find echoes in recent theories proposing that consciousness is a fundamental aspect of reality rather than an accidental byproduct of matter. Integrated information theory, OR theory, and other models suggest that consciousness is rooted in the structure and organization of information itself. A quasi-crystalline universe would provide a natural architecture for such integration, a non-repeating, richly structured lattice of possibilities where mind could emerge not by accident, but by necessity. Yet embracing this view forces us into strange territory. If reality is a projection from a higher dimensional quasi-crystal, then our everyday world is not the ultimate layer of existence, but a shadow cast by deeper structures we cannot directly perceive. Our familiar dimensions of length, width, height, and time may be emergent properties, not fundamental givens. Underneath them lies a realm of pure mathematical relationships, a hidden order whose symmetries and patterns define everything from the motion of galaxies to the firing of neurons. The paradox also challenges the notion of space having a center, a boundary, or a background. In a quasi-crystal, the pattern is everywhere and nowhere. There are no privileged points, no repeating cells to mark positions. Every location is unique, yet interconnected with all others through the underlying order. Similarly, in a quasi-crystal-based reality, there would be no center of the universe and no absolute space-time grid. Position and movement would be relational, defined entirely by the connections within the quasi-crystal pattern. Some versions of the quasi-crystal hypothesis are inspired by the work of physicists like Garrett Lisi, who proposed that the complex symmetries of certain mathematical structures, like the E8 Lie group, could underlie the fundamental forces in particles. Others draw from the study of quantum gravity, where space and time emerge from a changing network of relations among fundamental nodes. Still others explore connections to holographic principles, where information at the boundary of a system defines its interior dynamics. Critics of the quasi-crystal model argue that it remains speculative, lacking direct experimental evidence, and struggling to connect cleanly with the standard model of particle physics. Yet its conceptual beauty and its potential to bridge deep gaps between quantum mechanics, gravity, and consciousness continue to attract thinkers at the edges of physics and philosophy. It offers a radical vision, a universe not built on smooth continua or simple atoms, but on intricate, hidden patterns of astonishing complexity. The reality as a quasi-crystal paradox reminds us that our perception of reality may be as much a construction as a discovery. The smoothness of space, the flow of time, the continuity of existence, these may be emergent illusions, born from deeper structures as yet invisible to us. It invites us to imagine a universe where the ultimate substance is not matter, but mathematics, not particles, but patterns, not forces, but forms. And it forces us to ask unsettling questions about consciousness itself. If mind emerges from the dance of information within a quasi-crystal, then we are not isolated observers, adrift in a meaningless void. We are expressions of a cosmic pattern, threads woven into a universal tapestry that stretches beyond space and time. Our thoughts, our dreams, our very sense of being may be ripples in the great quasi-crystalline sea of reality. The quasi-crystal vision is not just a scientific hypothesis, it is a profound philosophical shift. It challenges us to see the universe not as a static machine, but as a living, evolving work of art, an endless, never-repeating pattern of staggering intricacy and beauty. It teaches us that reality may be far stranger and far more wondrous than we have ever dared to believe.